Okay, good morning, everybody. Welcome to the 2022 iteration of the virtual masterclasses for the AECtech Hackathon and Symposium. This is Parametric Structures course. Thank you for joining us today. I'm in the room here at New York, Thornton Tomasetti, with Aloy Kemp and Rob Otani, who are going to be the professors for today's class. This is us, Rob Otani, Thornton Tomasetti CTO, Aloy Kemp, Senior Associate, myself, Director of Core Modeling. Lots of experience with parametric structures, facades, complex modeling, and workflows in general. The agenda for today looks something like this. We'll do a brief 10-minute intro here about what we're doing and how we're going to be doing it. We're then going to have a sort of introductory session on the finite element method, which sort of underpins most of what we're going to be working on today using Karumba inside of Rhino and Grasshopper. The morning is going to be dedicated to looking at sticks. So we're essentially talking about frames here, beams and columns. How do we make them? How do we analyze them? How do we visualize some of the results we're going to get from the structural analysis? We'll break for lunch at 1 p.m. We'll come back at 2, and the afternoon we're going to dedicate to a little bit more sticks with the building, and then focus on shells for the rest of the day, finishing up with form finding in the evening. This is the software we're going to be using today. So we're going to be working in Rhino, which is going to be our 3D environment where we visualize things and sometimes build objects. We're going to be coding in Grasshopper, which is a node-based platform which allows us to do visual coding that ties directly to a 3D environment, being Grasshopper. We're not constrained to just geometry there. We can do things like read Excel documents. Most of the legwork here today is going to be done by Karumba, which is a plugin for Rhino through Grasshopper, which is a structural analysis engine that allows us to apply loads, restraints, fixities, run analysis, and get results back. We're going to be doing a little bit of work with Calibri today, which is a tool from Thornton Tomasetti, which allows us to generate data sets. Whenever we work in a parametric model, we're essentially enabling ourselves to create a large data set with sliders. So Calibri is going to be shown today as a plugin that helps us take our Karumba models and turn them into data sets we can visualize. There will be some use of kangaroo simulation in Grasshopper. This is another great plugin that allows you to apply physics-based simulation to 3D models. And we have two sort of external tools that are not tied to Rhino Grasshopper here. We're going to be using a little bit of Excel as an external data source. And we'll also introduce Thread, which is a web-based visualization tool, again, from Thornton Tomasetti Core Studio. Anyone who's used Design Explorer in the past will be familiar with Thread. It's the new iteration. What we're using today for sample files, so there is a Google Drive folder. Everybody should have access to that. Again, if you don't, please just throw it in the chat, let us know. We'll send you a link. Essentially, we have a folder with either 1 or 2, 3 maybe Grasshopper files in there, and possibly a Rhino file also, depending on the specific example we're going to be working on. So I would suggest just download the whole folder to your local machine. We also threw into that Google Drive a couple of useful plugins today. I did throw in links in the email to Kangaroo, Calibri, and hopefully Karumba as well. But if you have any other questions, just let us know. If you're missing something, we're happy to provide it. Okay, so we're expecting a variety of skill levels today in terms of Grasshopper knowledge. We don't do anything too intense in Grasshopper. Most of the sort of thought and knowledge is going to be on the structural engineering side. We do have a couple of scripts that are going to introduce data trees to people. If these are unfamiliar to you, don't worry too much. Everything's being recorded, and we're happy to sort of answer questions as needed. We do have a big group today, some 20 odd people. So, and we've got a lot to get through. we don't want to spend too much time if Grasshopper is your primary concern. We're happy to answer questions as need be. As I said, we're going to be utilizing Thread today. This is a web-based platform you can find at thread.thorntomasetti.com/welcome. This is something you will have to sign up for. And if you shoot us an email, hopefully we'll be able to give you access today if you sign up for it. This is only used in 1 or 2 of the examples that we're going to show today. And again, you can watch it on screen. If you want to use it yourself, you will need to sign up for an account.
In case anyone didn't get it.
Perfect. No problem. This is what Thread looks like. So, you know, it's basically parallel coordinates, charts, 3D visuals are possible. And we're essentially uploading images and a CSV file from Karumba to Thread. Okay, some notes on the units of the files we'll be using today. So Karumba was built in Europe. So its sort of default mode is metric. As we're in the States, and we've probably got primarily imperial-based engineers out there, all of the sample files we'll be using today have Rhino units set to feet, and the Karumba units have been set to imperial. So you're welcome to use metric if that's what you're more comfortable with, and you can essentially ignore some of the next slides that talk about altering the units. But just be aware, obviously, the numbers you see will be different than the ones on our screen. I should note that there is some warnings Karumba gives where files that have been built in imperial, if you open them in metric, you may see some interesting behavior, and vice versa if you start in metric and come to imperial. So I think in general, if the files today are going to work best, you will follow along with us in feet and imperial. I'll just point out here, Karumba has some really nice documentation online. Some of the stuff I'm going to talk about in the next couple of minutes has been well documented there. So this is a great resource for anybody looking to learn more beyond the examples we showed today. This is at manual.karumba3d.com. Huge thanks to the Karumba team, by the way, for all the extra licenses today. We very much appreciate that. The fact that if you've got the license file from Karumba, you've got it all month is super awesome. All right, so units. If you're installing Karumba for the first time using the MSI file that they provide online, then you are given an option at the install portion about what type of units you want to use. So if you're just installing it now as part of this sort of introduction here, I would suggest you switch this here to imperial units. So the type of units in the install to match us will be imperial units. And you are going to use the full mode today, either via the cloud license or via the local file. It's relevant here to note that, you know, this is directly from the Karumba manual. Once you make the switch to imperial units, like for example here by switching this button, all coordinates will then be interpreted to be in feet, force in kips, and material strength in KSI, etc.
Displacements in inches.
Yeah, I think there's a slide in here. So it says feet, but it can change depending on the thing you see. So if you've already installed Karumba and you don't have the option of setting the imperial units at the install portion in that previous slide, you can make this change directly to the Karumba INI file. This is found inside of your Windows program files, Rhino 7, plugins Karumba folder. This is where Karumba gets installed to when you use the MSI. And this again, this requires you to have admin rights on your machine, so it's not suitable for everybody on the call, which is why I suggest if you can to use the MSI and set the units here at install. But essentially all that we've done here is
I put in there in the section on the
system down here from SI
let's
to Imperial.
get
So
a
in this case,
spreadsheet template
the system is equal to Imperial SI.
and we'll just leave the items.
As Aloy mentioned,
Provided
once we make this
Yeah,
change,
that it gets
what we're
blocked.
doing is essentially changing Karumba's
Okay.
backend solution, the way it shows values that have been computed. This does not necessarily alter what the Grasshopper Canvas tooltip might show you. So for example, here in this define cross-section tool, if I hover over the height input, you'll see that it says centimeters here. This is sort of hard-coded as part of the tool. If I have changed my units from metric to imperial, this centimeters is replaced by inches. So any input here that's being put into height, in this case, 6 to 24 is a domain between 6 inches and 24 inches. So essentially, if you make the switch, ignore the tooltips is what we're saying. Okay, a general format for how we're going to approach the Grasshopper files we've provided today. We are leveraging a lot of what Karumba has provided very kindly on their website as example files. Essentially, what this breaks down to is a parametric part where we're building geometry or something like geometry. We then assemble an analysis model, a structural analysis model, and this is Karumba stuff. And then we eventually visualize the results of that analysis. We've tried to break out the files into sort of steps. So generally speaking, we'll start with a Grasshopper script that's defining a parametric model. And we'll talk through how you built that model, what the outputs of it are, what the variables that it can change are as part of that script. We've then got a next step, which will include the Karumba assemble analysis and visualize results. And if we do end up going further, there'll be a third script, which includes all parts. So we may have external data sources. We do have scripts that upload information to Thread. The goal here is essentially not confuse everybody with a complicated script to start with. We want everyone to understand the parametric part as well as the analysis part, independent of the separate uploads and downloads. Okay, with that, I'm going to turn it over to Rob Otani, Thomas City CTO, who's going to give a brief introduction to finite element.
Hi, everyone. So this, for many of you, I think, particularly structural engineers, will be review, but I figured I would go over this for potentially review, or if someone is not a nerdy structural engineer, at least has a basis of why we do certain things in these scripts with such rigor, I would say. So fundamentally, the FEA method is a numerical analysis, and it uses solves differential equations that describe physical problems, and anything from the design of the button on your iPhones to car frames to other fluid-based analyses. Finite element method is used, and today we're going to be doing more simple things like buildings. So really quickly, this is a demo that I like to show because I think it's sort of like the nth degree of, will this show up, Nick? The nth degree of FEA, which is a simulation and sort of side-by-side simulation in real time implosion of a building, where our core modeling team worked on the modeling of it, 3D geometry of it, and then our applied science team did the FEA. And now I'm going to go to the sort of highlights of this video. So basically, they did the simulation of this explosion, and it's pretty incredible what you can actually do with the right tools and the right methods. In this situation, we actually have an in-house tool that does some of this, but you can see that you can get very, very close to actual simulation, and that's sort of the nth degree of what we want to do in our design analysis for this essentially. So screw this up here. Okay. So as I mentioned, the key to this is understanding that the connectivity of all these models and the various inputs that we need to make sure that the output is clear. Fundamentally, the method solves this equation, which is equation of motion. Force equals mass times acceleration plus damping constant times velocity plus stiffness times displacement. What we're going to be doing today is really just the force equals kx, which is we're not dealing with things in motion, we're not dealing with things in velocity. So those things sort of cancel out. But that is the fundamental equation that we solve by doing this. And this is a very quick example of a truss problem with 2 degrees of freedom per node. Basically, we're solving this matrix where the stiffness is defined by these various factors, K11s all the way to the K66, those degrees of freedom, and then we back solve that equation to solve the displacements, which then can, sort of work hand in hand with the forces. So it's almost like an infinite chain of elements connected to each other that sort of like talk to each other. But the key is the connectivity, what we call displacement compatibility and force equilibrium. I mentioned displacement compatibility. That is a key component of FEA. So if you have nodes that are not connected, it doesn't understand that they are connected to each other, and therefore they won't transfer any force, and potentially could be also unstable depending on how that assembly is developed. There needs to be equilibrium, so we always need to solve for forces and being equal. And these are just 3 examples of FEA, which we are going to use some of these things in this class. So like the first one on the left is just a stick element, as Nick mentioned, 2 nodes, an element defined by the connectivity of those 2 nodes with properties or attributes assigned to that particular element. And you could solve, that could be a beam, that could be a column, that could be truss member or whatever. But that same beam can be also defined by shell analysis, which you see with the nice colors on the right. That is a meshed element. It's essentially doing a more detailed analysis of the stresses and forces within the body of that element. And the one below is sort of an in-between where I defined that beam as being 3 elements. So the top plate, the web, and the bottom plate is 3 separate elements, but fully connected so that it represents sort of the same thing. So there are multiple sort of flavors of FEA. Most of what we're going to be doing is stick modeling, but there is multiple forms. So this is just some examples, things that I've played around with over the years. Again, I think the important aspect of this is to understand, in order to optimize a structure, you need to understand how it behaves, how it deflects, where the forces are moving and going, and then you can start to optimize that form. Some more examples, projects in the past. I've taught this class at Pratt to architects, and I will say that some of the architects really gravitate towards this because they themselves as designers want to understand how to sort of what is driving the performance of the structure. And as you can see, I'm a huge proponent, I should say, of not just stress distribution visualization, but also deformation visualization. It is a significant sort of telltale sort of indicator of how the structure is behaving when you see not just the forces, but also the deformed shapes. Just some more examples. These are actually Karumba examples, by the way. Actually, the student is now Andrea is now a acoustic consultant, ironically, but she was very good at modeling. So this was former core person, Han Chen worked on this in my class. So these are the key components that every single analysis needs to have, which is obviously the geometry, node and element connectivities, materiality, you have to define the materials, work conditions, the loading conditions, those are the key components of any FEA analysis model. I want to stress that the models need to be clean. So Grasshopper is a perfect tool to ensure clean models. We'll talk about this a little bit later about discretization of certain elements. Most FEA programs do not like curved lines. So you have to represent curved lines as a sort of chain of straight lines. And for shells, this is just a pointer. Whenever you do a shell analysis, because it is defining the stresses through a certain medium, you need to have at least 10 elements through the sort of thickness or depth of the member to define the stress, because it's calculating stress. Typically, FEA programs define the stress at the center of the node based on the movements, the relative movements of the corner points. And so therefore, imagine if I only had like one block per the depth of the member, you're not seeing, you won't be able to see sort of what happens at the top face or the bottom face or the side faces. So this is a general rule for shell analysis, that you need to have a reasonable meshing density to understand the behavior of the structure. I don't want to get to this. I think that's the end. So again, this is mostly a review, but this is just kind of indicates why this class is going to be so dedicated to connectivity and clean geometries.
So the only trick here is that if you are looking for the cloud license, you will have received an email allowing you to join the Thornton Tomasetti group. Let me just quickly jump to that email. So just to review that, we've also got a Slack channel, by the way, everybody. If anybody has any questions that are not best put into the chat, looks like, all right, cool. So everybody has started to use the Slack channel. That's awesome. For those of you looking for installation instructions who didn't get the email, I've placed them here in the Slack channel as a chat. So there are three options. People with admin rights. So if you're able to have admin rights on your machine, this is the best option. And this basically would involve you grabbing this LIC license file and then going through the standard installation instructions. If you do not have admin rights, then the options are the accessing of the cloud licenses, which would involve you opening this link and following Karumba's really nice instructions. First step, install Karumba. Second step, when you go to get a license, you're going to follow through. You're going to need to create a Rhino account. And when you get to this step and you add a license, this is going to be, once you've accepted the Thornton Tomasetti team, you'll be putting the Thornton Tomasetti team in here and then using the license key that came with the email. The last option is the standalone license. The second option is the standalone license, which we talked about, which involves you essentially just downloading this file and installing it. There are some other plugins that I've put links to here. As I mentioned, we are going to be working with Kangaroo today. This can be had on Food for Rhino. No need for admin rights for this. This is simply something that's placed into the Grasshopper folder. You're also going to want to download Calibri, which is a TT tool from Food for Rhino. And just to clarify, in the Google Drive folder, you should see something like this, which includes numbered folders for each of the examples we're going to go through today. We've also thrown in here a couple of other plugins that you may want to grab and place into your plugin folder. This includes the TT Toolbox, Human Plugins, and Uto Meshing Tools.
Have you already called the license?
I have, yes.
Okay, so Nick has already typed in Karumba. So we can see that the license has been initialized. And one way that you can tell when you open up Karumba is, yeah, I'm like looking for the other K, is if you grab this button, license, and you put it in the canvas, it should tell you what kind of license you have. If you don't initialize the license before you open the file, it's no problem. You may notice some tools are red. You might open the file, you see a tool is red, and you go, oh, I forgot to initialize the license. You can go back into Rhino, initialize the license, and then you just have to click on the tools that are red, right click, disable it, and then click again to enable it, and that should reset the file. All right, so we're going to start with some simple beam examples. If you've downloaded the files, we've roughly tried to make the folders match the agenda, although the file names within may not entirely match. So first we're going to start with a simple beam. So I'm dragging it in. And I'm going to open up the perspective view. Oh, I'm also going to open the Rhino file that goes with it. This, for most of the files that we're using in part in the morning, I think all of them, at least on my part, are using the same Rhino file, which is called input surfaces as shell. Ignore the name. There's just a couple objects in this file that we can use later. So for completeness, I'll just select all and hide everything in Rhino space. So we can get a good look, a big overview of this pretty simple model, and we're going to dive into the parts. So initially what we have here is a line in Rhino Grasshopper, starting with a point, which is referenced in, or I think this is internalized from Rhino, this tool, which is called SDL, line start direction length. And the variable is length, which we've included as a slider. And you can see I can make it shorter or longer. Then just a useful visualization is to take the endpoints and draw a dimension. Is this a human tool?
No, it's a new display tool. If you do
okay.
Control Alt left select, hold down at the same time.
There we go.
So Control Alt left select.
Control
will tell
Alt
you
left select.
where the tool came from. So this is a new display tool. It's up under the display tab in the
Nice.
dimensions.
I knew there was a way to do that. I just couldn't remember how to highlight where that tool came from. And that's it for Grasshopper. It's really just this portion. We're just drawing a line, getting the two endpoints. Then, as Nick said, we're going to start the Karumba assembly. So keep in mind what Rob said earlier. We need geometry with sections. We need materials. We need loads, and we need supports. So the first thing we're doing here is, on this side, is defining cross sections. Karumba has a couple tools under this cross-section tab. And typically I use this one cross-section range selector and cross-section selector, that's what these two are. This is the range selector, and this is the cross-section selector. So really all this does is when you choose the country, the shape, and the family of a cross section, it gives you a whole list of elements. You can see in here the name is W4x13, 6x16, 8x13, et cetera, et cetera. This is called material select in Karumba. Again, they do have a there's material properties selection or read a table from file. This is simply just called selection. The family is steel, and the name is 355. They do have AECtech steels, but I've been getting some funky results with that, and I know that S355 has 50 KSI. So that's what we're using for these demonstrations, but it's just something to note, perhaps because it's originated in metric European circles. The troubleshooting with American sizes and materials isn't quite there yet, but it doesn't really matter as long as the KSI and the E are the same, which they are. We're using another slider here to select which cross section from this list. Obviously, we don't want to apply the whole list to one beam. So we're selecting one by using the index, which is its position in the list, to grab that particular cross-section. So this input is asking for a list of cross-sections. Then it says, please define by name or index. And then this is the identifier of the element of the beam to attach to, which is optional in this case. And then it asks for a material. So I'm just going to demonstrate that. Quick little list management and understanding. So I'm grabbing index 24. Go to 24, we have W 10 by 12, and that is what is being grabbed. So we've chosen a section. Now we need to apply the section, and that would be this button, which is called Beam Line to Beam Karumba 3D, and that is under the Model tab. So that's Line to Beam. And so the input here is the line, which is grabbing the line that we drew previously, which is here. This is optional to give it a color. We gave it a name. We're explicitly naming it. If you don't do this, Karumba will name it for you. But we found that when we're putting these scripts together, if you ever need to call something later on after you have results, it really does help to name it beforehand. And in other scripts, we can show you how to make a more dynamic parametric name for a whole set of objects. And then it's asking for a cross-section, which we put into the cross-section selector that we just went over. The next thing we're going to do is supports. So under Karumba support, I believe it's under model. Yes. So support 3D. This is pretty simple. I would say if you're familiar with any sort of analysis software, this will not be that confusing to you, except perhaps just the names of these. So translation X, Y, Z, rotation X, Y, Z, and what plane is it in? So if you wanted to have a different plane other than the one that's in Rhino, which we can see with these axes, the red and the green. If you would like a different plane, you just simply have to define it. But in this case, we're just keeping with global coordinates.
So it's a global XYZ.
Global XYZ is default. Global in Rhino. So one thing that we haven't checked is what if you change the Rhino XYZ? Does that change it in Karumba?
Don't change it.
We're not going to try it. And then it's asking for a position or index. So input index or coordinate, I suppose if you had a list of points, you could select the indices, but
The output of the line to beam gives you the points.
yes,
So you could take the points from
Yeah.
that component.
yes, you could select it from these points is what Nick is saying.
Yeah.
So he's saying, yeah, you could select it from these 2 points that are the endpoint. However, we're grabbing it explicitly from this tool because we know it's the start. If you notice, it's only going into the start output of the curve. And where that exactly is, that's right there. So it's closer to the origin. Great. And we're giving it full fixity. The third thing is loads. This is interesting because, and ignore this part that says old. I believe this is probably just because I built it in Rhino 6 and now it's in Rhino 7, but it is the same tool. So Karumba really has only one button for loads. It's under section 2. And this is where you define all types of loads. So a gravity load, just ask for a vector. Point load, ask for a force, moment, local, et cetera, et cetera. Any type of load that you get, you select with this drop down. This is something about Karumba that's very different from other plugins, or if you're an experienced Grasshopper user, you might get stumped by this, as I did when I first opened Karumba, because you expect the tool to just be what it is. But basically, if you ever see this type of slider or interface with a Karumba tool, it means that there are other options and the whole tool may change. You can see the inputs are changing as a result of this. So we grabbed a point load and we want to put the point load at the end point. So you can see that the wire here is only going to the end point of the beam. And then it's saying, what is the force? And it's asking for a vector with a magnitude. So we're just saying a 10 kip This is in KIPS. This tooltip actually has the right units. So it, as Nick mentioned, sometimes the tooltips change, sometimes they don't. Can be confusing. Just use your common sense, do a hand calc if you're really worried about what value you're getting. And then it asks to define a load case, which we're not doing because we're only doing one check, but you have the option to do that, and that creates your load. So now we have a beam, we have support, we have load, the material is over here. The next button in Karumba you'll need is called Assemble Model, and that's under tab 1, Assemble Model. So it's asking for all the pieces that are that comprise this model. So the elements, I believe this always needs to be flattened. Otherwise, it's creating two separate, for any number of branch in a list, it'll create a separate model, I believe. You can pull them out. That's why naming them makes sense. If you have a bunch of different branches with names, then you can get them again in those branches later down the road. We've got one element, we've got one support, we've got one load. We've linked this. If you've already applied a cross section to a beam, you don't need to link it back to the cross section. This comes into play when you're trying to optimize a beam or optimize the structure. Nevertheless, it doesn't hurt if you insert them here. If we had any member releases, they would go into joint, and we'll get to that later. And that creates the model. It's assembling the model. At this point, you can actually use this viewer, which I've done a couple times before, to make sure that your model has assembled correctly. So if we right click on it and we want to preview it, what you can see here, there are all these checkboxes. So I'm checking that this model hasn't been run yet, so it won't show you deformation reactions, but it will show you load. So if you uncheck that, the load goes away. If you check it.
So you better put it in a position for your load, right? So you're.
She's putting it in the end.
This one's a cantilever
Oh,
beam. Yeah. Local axes, we can turn that on, and you can see that the beam local axes is showing up in the center. Also, what we've turned on is supports. So what support will do is it'll put a green arrow wherever there's a translational restraint, and then a purple circle wherever there's a rotational restraint. And that's under supports, and this slider chooses the size of it. We can have node tags, and you can see what name Karumba has given the node. Element tag is, if you turn it on, it'll say 0, but I have turned on element ID, so you can see that it has the name we gave it. You can turn on all sorts of other things. Load values, I like to turn on. If you, here's a tip. When you open up this tool, for some reason, this button elements isn't always checked. If you uncheck it, let's just say you actually have Grasshopper turned on. If you uncheck elements, you won't actually see the elements. Now, why is that not a default? I'm not sure, but please check that, and then you can actually see. You could say color by cross section or material. This sometimes works, but anyway, so to just check that you've got all the pieces in your model you want to run. To analyze the model, there are a couple different options. They have algorithms. They've got analyze. You see this little 1 in the corner, 1, 2, 3. This is second order analysis, and this is non-linear, but it's a work in progress, and then large deformation, which we'll get to at the end of the day. But for most of these things, the first order is sufficient. So we just put it into the assembled model, and what you'll get out of it is a RAN model and an output of the maximum displacement. So here's an example of where the tooltip doesn't match force or doesn't match the actual measurement. This says centimeters, but it is inches. So this beam that we're getting is actually deflecting 567 inches. That's quite a lot. How can we see that? So you just use this model view and you link it to the RAN model. And now you can see the beam has deflected. And you can see the beam has deflected. You can also see the reactions, which I've turned on. Do it. On that. And yeah, you can scale the deflection more or less with this. Obviously, this is deflecting a lot, so we don't want to have it appear out of view. And then this is a third way to visualize the models, and you'll get very comfortable and very familiar with these like 6 tools because they appear in just about every script we're showing today. This one is called Beam View. There is another that appears under results. There's another one called Shell View. There's a way to get more information like beam forces, resultant shell forces and such. But for just a basic, see how you're doing, Beam View or Shell View is quite good. So we'll turn that one on. So number one, so right now the deformation, nice to just put it on 1. It's hard, it doesn't really snap well. Okay, there we go, we got 1. So under here, we can view forces, we can view by stress, we can view by displacement or utilization. So under displacement, this shows up like what you'd expect, the most there, the least here. And for any one of these render settings that has a range, that has values associated with it, you take the legend tool, which is a Rhino, what was it? You said Control Alt left click. So that's under Rhino graphs, right next to the preview near the dimensions. These are all display functions. It looks like this at first until you link it up to the values and the colors and the values. And then if you hover over the bottom, you can drag it down. What's nice, it'll automatically give you a little title at the top. If we look at utilization, it says it's 3,300% utilized. That's not great. We definitely want the deflection to be less and the utilization to be less. So I think we should choose a different cross section. Let's see, now we have a 12 by 170. Reflecting 18 inches, which looks pretty subtle in this viewport. And the utilization is pretty low. But you can kind of see how fast Karumba is at responding to these changes. And obviously with a simply supported beam, you could build a MathCAD sheet pretty fast too. Yeah, so we can exaggerate the deflection. And then this is model view, which is sort of viewing the reactions, deformation supports. You'll notice that if I put this into the actual model, it'll always show the deformation at 1 or maybe 0 actually. And then if I put it into the model view, it'll show the model drawn as a solid where the deformation is linked to this slider. So yeah, it's pretty fast. This is probably the simplest example you could think of. You can also check it with a MathCAD sheet, which I did, to make sure that these were indeed inches and that the forces actually made sense. What's also nice about this is, although we've applied, we've just had a stick where we applied a member section to it, you can see the utilization is actually colored according as if this beam is broken up into separate meshes. So it's not just giving you one, it's actually showing you that at the neutral axes, the utilization is 0, and at the top, it's in tension, at the bottom, it's in compression. They're two opposite ends of the utilization spectrum. So you can see the top is negative 8 points, or the bottom is negative 8.6, so that's compression, and the bottom and the top is 8.6 blue. So that's a nice handy feature for Karumba. And yep, this is just an intro to how well it can visualize things. So we're going to do a couple more beam examples, but these will probably go a little faster now that we've introduced the tools.
Nothing in the chat. Any questions out there on the first example?
Any questions? You can type in the chat. I think Nick is monitoring it from my screen on the other side. All right, now we're going to try a simply supported beam. So this has slightly more, this is what we're going to get to, is a deflected shape with actual values. So I'm just going to turn off the big reveal, and we will build up to it. So first we're creating a geometry. This one has a line. We're not making the line the variable in this case. We want to show some other things. We have a dimension the way we did in the previous model. In this case, we are actually breaking up the beam into multiple smaller segments with this tool called shatter. And shatter asks for parameters. So I'll get to where those are coming from. One thing that, or where those parameters are coming from, they're coming from two different sections in here. So first of all, we are, the system that we're trying to define, actually, I'm going to turn this one really quickly. Oops. Not used to Nick's mouse. The system that we're trying to define here is a simply supported beam. So it has a pin support here and a translational roller, but rotational fixity at this support, and then a free end and a distributed load across the whole top. That's what we're trying to get to. The first thing is we want to define the position of that middle support. And we're using this by taking a line, a curve to evaluate, and then evaluating a parameter along it. So the length of this line is 10 feet. You can put in a parameter that corresponds to a position, but it's a little odd if you right-click and reparameterize. This should change from, oh, it only went to 0.5. That's why. Yeah.
Lines do not need to be reparameterized. Lines are
That's a good tip.
0 to 1.
Lines are always 0 to 1. Other types of curves in your Grasshopper life, which is, I suppose, what I'm used to, if you want to define an actual, if you don't right-click and reparameterize, which makes start 0 and 1, this number refers to an actual absolute distance. Again, we're grabbing the endpoints of the line, and you can see that we're only taking the start point and giving it a pin condition. Then we're taking this found point and we're giving it translation Y, Z, RX, and RZ, rotation Z, and we can play with this and you can see the results. And then just to make the script a little cleaner, we're grabbing a button called support. So under the Karumba tab, under params, they've got cross-section element, element set, joint, load, material, model, and support. This is useful when you're trying to gather a bunch of different elements so that you don't just have a ton of wires coming out of your assemble model. That's what that button is. Another thing we're going to do here is define a load. So again, we're using this position to define a point load, and it looks like, you know, the creators of this file are letting the point load go anywhere on the beam, which is cool. But the support can only go from midpoint to the end. And they're giving it two different types of load, which is a point load here, or a point load called load case 1, and then a uniform load that we're calling load case 2. So again, the load component from Karumba looks the same. It's just that in this case, they selected point. And again, we gave it a vector. We said it's 5 and Z, and this is just making that negative so it goes down. The line load, it does say, because this file originated in metric land, this is in kilonewtons, but really, if you hover over it, it's asking for kips per feet. So that's what we're giving the uniform load. And we're selecting a cross-section the same way we did before, steel, but this time steel IW. This is the index we're grabbing, and then I just have a little output showing what member that actually is. So let's get to a nice 8 by 10. All right, so we have our beam line with a name. We have a cross-section applied. We've got a couple different support conditions bundled here, And we have a total gravity load, which is defined as load case 0, a point load, which is load case 1, and uniform light load, which is load case 2. And all those are bundled together in a parameter called load, which just gathers everything. And we're assembling the model with that. I'm just going to use a model view quickly to show the built model. So again, if you open all of these things, for some reason, okay, this one element is turned on. I like to turn on the load value. You can see that the point load is right in the middle there. Let's make this a little smaller so that we can see them better. You can see gravity always shows up as just kind of a generic 1.0 going down. And I believe that it is accurate to the units. So in metric, it's 9.8 meters per second squared. And in imperial, it's 32 feet per second squared. And that's something you can actually see in the text file that Nick was showing earlier. It does calculate it for you. So even though it says 1, it is appropriate to whichever unit you've selected. So when we actually hook this up to the analyze component, the first order analysis, it gives us 3 different displacements for each load case. So that's useful. And we'll show where this comes in with this component, the model view again. So now we're hooking up the model view to the actual run model. And you can see the deflected shape. And we can still scale it however we want. But down here, it's asking for which load case do you want to view? So if you remember, 0 is gravity, 1 is a point load, and then 2 is the distributed load. And you can see the load viewer also changes as this changes. And then our tried and true favorite visualizer is the beam view. In this one, we're turning on some extra things. So first of all, we have the utilization. We're saying render it by utilization, and here's our legend. Make that a little bigger. It might be a little more readable. So it looks like it's going from 34% to about 34% in both directions. But what's also cool about this tool is you can turn on the forces using these buttons down here. So in the previous example, we didn't turn it on, but we could have. You can show axial force, shear. I guess it's not showing up super well. Here we go, shear VZ. You might take a couple tries to realize which direction is Karumba referring to. And what's nice is that the values actually follow the deflected shape. So as long as you've linked the beam view into the model view component, it'll follow this. If we link it directly into the RAN model, it's showing all 3 things at once, I believe, because it doesn't know how to differentiate. And there's no load case selector down here.
So the directionality of the moments.
Directionality of moments is based on global coordinates. So MX would be a moment about the X axis, which in this particular example would be torsion. So this is why the MY is showing up, because it's a moment about the Y axis. So, we're doing a 2D analysis in the XZ plane. So what you will be seeing is MY in this particular case.
Yeah, so someone asked, how is utilization calculated? Is it stress over yield? To be honest, it's giving you the utilization for everything. So I think if you were looking for stress, you're going to find it. You're going to find actual stress here, but then they break it down per individual force component. So this part is similar to the way SAP would calculate it.
Yeah.
And then this is a combination of those.
I believe it is in the Karumba documentation. It's a stress-based calculation utilization.
So we've got 3 different things for the first, but this is where I, maybe with a grain of salt, it's basically saying if you take this output as true, that under the gravity case, it has a utilization of 1.4, which I don't believe. If you put it in the slider here, it goes from 2.7 to 2.7. So, more investigation probably necessary. Try it with a hand calc. And I think,
I feel like it's just gonna be reversed, right? That the lowercase 2 could be in the first item. I mean, it's weird.
that would be weird. So Nick is suggesting perhaps the load cases have gotten
Because they're
switched.
factoring up, right? I mean, that's, you'd expect the last load case to be the one with the closest.
Yeah, it is in largest to smallest order. However, this number doesn't seem to line up with
No,
this.
yeah, I wouldn't use that. I would use the,
So this goes from 9.2. This is nice, but in other documents, I do want to use this. I would love to use this to actually pull it out. And it did make me a little nervous for a while about it. You can see it's driven by MY, like that value doesn't really change. Where's VZ? That
go to VZ.
that number doesn't really line up with this either.
At least they're relative, like it's just the utilization that looks off, right?
Yeah. I could check my notes during the lunch break, but I did push a couple things into SAP directly. And I believe I was getting exact results with the legend viewer. Just a note, but that's kind of where I stopped. I wanted to verify the scripts that we had and wanted to show you guys. But yeah, this is it's calculating something, and maybe we can spend a little bit of time to figure out why, but
Yeah,
hopefully
can
that
you turn off the color and just show the utilization, or will it not show anything?
like that.
No, the color, not the color models, the color legend.
Like the reactive white,
Yeah,
we won't show anything. There's nothing there to
you get
show.
little numerical values that should.
It's not showing the utilization numbers.
There's no numbers for utilization, it's just a mesh. Call it mesh.
The only other thing I can think of is that this is more discretized on the beam, whereas this is just giving you a single value.
Summed up, yeah.
That's the only thing I can think of, but we would have to investigate a little bit more. Okay, so that is the simple beam. Oh, looks like they're also doing a little bit of display, which is mostly Grasshopper. It's not really Karumba, but we're using this tool called beam forces. We're linking it to the model. We're not giving it a beam ID because we're asking for all the beams, which is really just one beam. But it is giving us, if I simplify this, so another list management exercise here. You can see that there are different branches of this tree. So if I hover over this, I see, it's hard to see, but we've got 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. The numbers within them seem to be always the same. It goes 77, 26 of items. So I'm guessing that either the first item in the first number in the path is the load case and the second number is the segment. So there's a first segment between load case and the point, and then the point and the support, and then the support and the end. But we just want the max here. So I'm not really interested in figuring out what is where, but this is essentially what you would be wanting to get from the, well, actually we could probably figure it out. So load case 2 is the distributed load. We can see that the loads go from 0, 5.2, 8.9, 10.42, negative 1020. Where are we actually seeing that in the list? Is this it? This is broken up into bigger sections. So I believe, yeah, okay. So I'm looking at load case 2. That corresponds to branch 2. But in this case, what we're doing is we're just grabbing the maximum bending moment. So we're sorting all of them. This is a handy component that we're using somewhere else in other scripts, but we're flattening the list. So we're taking all the parameters that are coming from this list. We're using this button that creates an absolute value under math. Then I'm going to use this all the time. And then we're using a sort component, which is super useful. What do they call it, Nick, when you can add the buttons? They have a funny name for it.
More parameters.
Yeah, variable parameters. That's what Rhino Grasshopper calls it. But this is essentially K is the key by which you want to sort a list of items. A is a bunch of items that you want to just follow that shuffle. So it's kind of like when you're in Excel and you've filtered a bunch of columns and you want to sort by one column larger to smaller, and then all the rest of the items on that row just follow along with the column that you're sorting by. Another handy thing is that you can actually change the name of this. So we're saying forces. I think that's what we're sorting by. And then I don't know why they're saying that the absolute and the positive negative is okay. So this is the absolute value of the forces we're sorting. So we get actually the minimum. So you can right click on any input and change the name. Doesn't always change on this side. And then this is the actual forces. This button is called list item. It's just choosing an item in a list based on its index number. So an index number is this number that appears on the left side of the panel. This is the address. This is the item here. And they want the maximum. So by default, this sort component does from smallest to largest always. So they have a reverse in here. I'm going to put the reverse in here so that we can actually see the output. So if you right click on the output, you can reverse it, simplify, graph, flatten, those come useful. But if you reverse it, the top number is actually the greatest absolute value force that we found. And we want to just grab that top line. So this is saying item index 0, and it's only grabbing one number. And then this part over here is doing something interesting. Usually, in Excel, when you want to combine text and numbers, you say that quotations and this, and that's essentially what they're doing. This is a very Excel-based approach. Just want to point out that Grasshopper has a button called concatenate, which essentially does the same thing. You could put in a text string, and this is also a variable parameter. You could add as many different strings as you want together, and it'll create a piece of text. So they're creating a piece of text here, piece of text where they're grabbing the maximum displacement, and then we're adding a text tag 3D, which is oriented in the XZ plane. So you can see that if I viewpoint, you have a target macro on here. Okay. Because zooming around is.
Oh, it's hard to locate center on something.
Yeah.
Usually I use click on the text and Grasshopper and zoom to that. It'll center the Rhino camera. Middle mouse button on the text component, and that bottom right is a zoom to.
Which one?
Yeah,
This one?
right. Yeah, the little red one. So that's now
Oh, wow.
focus the object in the Rhino.
Oh, it did. Wow. I've actually, see, I learn something
Pro
every
tip,
day.
So middle mouse button.
Middle mouse button on the component, and then you bring it over to here and it'll Rhino zoom to that object. I will say Grasshopper has come a long way. There are probably some things I should say that's up front is that I'm still used to doing it in a certain linkage of nodes, and then later down the line, Grasshopper has made a tool that does just that. And I've had new Grasshopper users just point that out to me, and that's okay.
Should we change the unit? So what we're seeing on screen here is kilonewtons, centimeters. As we discussed earlier, we've changed the unit, so the sample file is no longer accurate. Super easy though. You just have to edit the
You got to click over here. I think it's taking your.
Yeah, she just has to edit the expression designer as you saw on the screen, and it's just going to alter the text.
But I forgot to put it in space, so now it looks weird. There we go. And then instead of centimeters, we want this to be inches. Bingo. Oh, that's nice. Another, I mean, we want to get really fancy. This is another tried and true, this is called swatch. And I just want the text to be black. That looks great. So, I mean, if you had an indeterminate structure, you could set up a beam check in Karumba and get a nice diagram from it. We're going to go to the third beam example. And I'm trying to do this really fast because I think we have a lot to get to. All right, so the third example. This one, I just want to, this one's similar actually. The other one might have been more complicated, but this is a good lead into, we'll probably revisit this when we link shells and beams. We'll probably revisit both of them or just ask you to remember them. But this is probably a good example where we can show some other visualization options. This one, oh, difference with this one. So this one, we're actually taking the beam. Sorry, let me just jump back because I forgot to explain what this was. We did say that we were going to shatter the beam at certain parameters, and the parameters we're shattering the beam are at the position of the support and the position of the point load. And that's why the output always had 3 different segments. It had start to, if the support was in front of the point load, then it's basically like putting these 3 points in a line, sorting them by their order along the line, and those are the 3 breaks. In this example, we're doing it in a little more organized fashion. We are actually breaking up the beam into a bunch of separate, this is the same beam from before, and we're breaking it up into a bunch of separate pieces. You can see all of the segments that are there. And this tool is called range. I don't know why it struggles to show the tooltip. Range of numbers. So it's asking for a range of numbers. The domain is 0 to 1. This is something you'd input, but by default, it's 0 to 1. And again, Nick said with a line, whether you reparameterize it or not, parameters are automatically assumed to be 0 to 1. With other curves, you do need to pay attention to that. So the domain is 0 to 1 by default, and we're saying number of steps, 18. And that outputs a list of steps to get 19 different numbers, 18 different spaces, to give you a list here. And you can see the segments there. The other thing we're doing, so we're taking that beam, taking that line, assigning it to be a beam with a name and this cross section. The only thing that's different about this from the other scripts is that we're just grabbing a circular section. You can see these fun inputs. I think this is a Rhino 7 component because when I open Karumba and Rhino 6, I only get this one option, HSRO. So perhaps there are some slight differences between the two. And we're grabbing the first item, but you can see the name of it is changing. This is another funky units thing. These are in millimeters. Hard-coded. So even though we're saying a US circle, this is 48 millimeters and the thickness is 3.7 millimeters. So that's a pretty small tube. Let's make this a little bigger. So if you guys are familiar with these number sliders, we want some more options. We're defining the supports at both ends this time. So in this case, the beam was defined by 2 points, and that's really nice. We can just put them both into supports. But we're explicitly defining a plane. We're explicitly saying that it's coming from, this tool is called get horizontal frame at a curve parameter. So it's parameter 0. Again, you would reparameterize this if it was anything but a line. But let's say your line was in space or it was tilted or something. This would make it not, this would make the support relative to that line. So if that line is actually in Rhino, darn it, that should have followed.
Okay.
If
But
it
the
did,
frame
but it
is a
didn't rotate.
horizontal frame.
Yeah,
It's
it's
a different way to
okay.
make the frame.
This was from Karumba, or this came in the file, but yeah, we could say perp frames. Perp frame would do it. I think that, I mean, that might, should we wing it? Should we try it?
Let's try it.
Let's try it.
Rearrange.
If we want it to be flat, we can also just change the things in the
So I think
conditions.
it's gonna be curved to the curve. You then have
Yeah.
to rotate it to the-
But we have translation in all 3 directions.
Hmm.
So it might be, okay.
Skip.
Okay, well, we're going to skip that for now. Let me just move that point down.
Just Control Z back in Rhino.
That's really weird. Now the point is gone.
Rhino and Grasshopper.
That must be a Rhino
It
7
was in
thing
the-
too. So another Rhino 7. And
No,
move
you
it.
have to grab it in Grasshopper
Mhm.
and then use the handles.
Yeah, but you can't snap it too.
No.
So if you grab it in Grasshopper, it appears in Rhino as something snappable, which is cool. This is close enough. Rhino 6 doesn't do that. You'd have to have it explicitly defined in Rhino for it to appear like that. We're defining the sports with a plane. As we were just hemming and hawing about, you could make it more interesting by actually tilting the model and then doing that, but regardless, that's how you do it. We're giving it a uniform live load with a value, and we're assembling the model. What's different here is we're actually going to try to optimize the cross section based on the element IDs. So the line that we're giving it is actually a bunch of segments. We are giving it just one name. And then this button is called Optimize Cross Section, and you would plug it in after the model's been assembled. So it's grabbing a list of cross sections. We gave it an initial one to start, but we're giving it a list. So this is something that you can read in the Karumba notes, but by optimize, it means it's just going down the list to find the next thing that works based on the criteria that you've given it. So the order of the list does matter. If you wanted to optimize by shape diameter first, you have to make sure they're organized that way. If you wanted to optimize by weight, which is oftentimes the case, you want to organize that way. The order of the cross-section list is important here because that's the way it's going to choose the optimum cross-section. Then we've got some other utilization max that it's trying to hit. You can play with this target value. Let's just make it 95%, give us a little fluff. So one way to grab a panel in the Rhino viewport really fast is to double click, put in the quotations, and then type in whatever text you want to appear in the panel. Then it's saying maximum displacement. This is an actual value. If you say -1, it means you're not trying to solve for that. But if you actually had a displacement you're trying to solve for, you would put that in there too. And you can see the displacement is 5. So I wonder, I mean, if we put in 3, it's getting 2.959. So it's trying to hit it. This is a pretty useful button. And then this is essentially an analysis. You don't need to link it between, this would actually just analyze the model the way it is with the section we assign. And this is checking the force flow through the beam and choosing the appropriate section for it. So let's turn on the model view. This is what we're seeing at the end. We can see the the loads. I want to, where does it say tags? I want to see load values there. And we have our deformation up to 20, but we can, change it the way we normally do. And then this is put into this viewer, the beam view, which we've used a couple times before. And you can actually see it's kind of subtle, but you can see that there are different segments with different size tubes. And so it is choosing them. One way to actually figure out what size did it actually pick. The different K. Is to use this button called, I've used this a couple times. Takes a couple steps, but it's called disassemble model. And you would put your run model in there and you'd get some beams. It gives you all the elements of the model that's been ran. And then underneath this tab number 1, you can also do disassemble element. So from there, we can get a list of the element IDs. I guess they're all called beam A, which is interesting. And then all the different cross sections that are applied to it. If you just wanted to get rid of all that extra text and only see the section, you can use a third disassemble, which is disassemble cross section. You would put that into cross section, and the name is just the name of the section. So here we can see the range of different sections. I think would be, there we go. That's even easier. You can just turn on cross section names in the viewer and you can see the sections they chose. So this could be a good checker if you want to create a tapered section. If it's known loading and it's going to be repeatable, but most of the time we're not really building custom beams for every beam, even though it might save you a little bit of weight. So that is the last beam example. Does anyone have any questions before we move on to trusses? Go to the chat. There's a question. Is there a way to use US codes? I doubt it. Yes, for steel structures. Yeah, so unless you want to look that up, no. The way that I would control that is probably using a max utilization. If you know that this EC3 tends to overcount or undercount DCR compared to whatever code you're using, you could probably try to control it this way. Or you just make sure the list that you're putting in makes sense. But in the end of the day, you're not going to use Karumba. The idea for Karumba is not to be using it for construction documents. So I would think that one code is probably close enough for the value that you're getting for how quick and speedy this will give you results. You can find a tapered cross section, you can put it through SAP and actually check it to verify your results.
Here it's stated slightly differently. That's the way we use it.
That's the way we
I'm
use
sure
it.
there's
Yeah.
some people that use it all the way till the end, but we use it for parametric studies, early design, comparative optimization.
It has a reasonable degree of accuracy. As I said, I did check some of the simple stuff with the hand calc. Some truss examples we're going to show in a bit. I sent a couple choice ones to SAP and compared them. So I trust it, but I wouldn't do a construction document set through this or a calc book with this.
The other thing that I would mention is that Karumba, we spoke to the developers, and the next version will have load combinations available. So that is sort of also a telltale sign that why we don't use it for CDs is because we obviously have to use load combinations. So in detail. So that's coming in the next version. So maybe it can get further down the path.
I have a hacky version of load combos in a later script, but it's not central to the script. So if I just gloss over it, someone remind me, and I can just show you how to set up a load combo in a somewhat hacky way. Right. So that's that. Any other question? Oh, we got another comment. Can you tell Karumba to use the largest cross sections at all? Well, in that case, we wouldn't be using the optimizer. So Michael's question is, can you tell to use the largest cross section? Are you saying that it wants to be the largest cross section that works? If that's the case, you would just turn these down to, I mean, you just wouldn't shatter it. You would just have one beam. You know, what we're specifically showing that if you break it up into separate beams, it'll give you separate results. You can still use the optimizer to help it choose, but it would just be a single beam, not a bunch of different segments. Are there any other questions? Those are good questions. But yeah, in general, you know, anyone who's worked on a project that actually got built knows that if you sent a contractor a truss with, you know, a bunch of different kinds of trusses that all have different chords and verticals and different chords along the length, they will probably be really, really mad at you. So it's not practical, but in some cases, it can be good to show it. Also, showing architects the effect of inputs is really effective with this. And you can, if you don't trust Karumba, just make the maximum utilization 0.5 or something, and you'll know that it'll be a little bit more conservative. But you know, hide that from architects, I guess. The group input, probably yes, that would also work. Okay. Moving on to trusses. So far we've been just doing single beams, and we will be moving into multiple beams linked together in more of a system. Yeah, let me hide this for now. Used in a later script. Okay, so the way this example file, you can download this from Karumba 3D, but there are a couple of interventions that we at TT have put in here. But generally, I've tried to keep it as close to the example you can get from the internet as possible. So we're taking a line input. This is referencing a line from Rhino. I believe it's internalized. No, it's not. So you do need to have the Rhino file open with it. Again, we're getting a mention, but for some reason it's not showing up very nicely. Oh, the size. 0.2. Okay, there it is. Have units in here?
It's running. So that's feet.
No, all right. Very, very long truss. So this button is from the TT toolbox, right, Nick?
Mm-hmm.
Yep. This is from the TT toolbox. It's called, yeah, let me use my new favorite tool, Control-Alt-Click.
Doesn't work on our components. Not on the native tools.
Okay. That locator tool does not work on TT toolbox. It only works on, where is it? It's under here. It's under structure. So if you download the TT toolbox, this is the older one. We will show the same stuff. The newer one has nicer looking icons, I would say. There are a couple different truss options. One is truss from two curves, so they could have different, you know, it could vary in height and width. Another one is truss from polycurves. This one's truss from curve by offset or polycurve by offset. I think we'll probably see a couple different versions of these in the scripts today. And also truss type, which is simply just a value list that we've pre-populated with a bunch of different values. Something that, because this is a value list, you can actually edit it yourself. And for the purposes of this demonstration, which we will explain a little downstream, Nick and I have removed Vierendeel from this list. So in the original one, it's there, but if you don't want a certain truss type to be available as a choice, you just delete it. And that's what we've done. I'll explain that later. So this takes the top truss and takes the truss height, which is a slider, and you can see there it goes. I actually think I want to make this line not so long. I just made it match the original. I just made it, oh, sorry, this isn't my computer, so all my shortcuts are, I'm just going to make this 100 feet. There, okay. 100 feet long. And we have the truss height is 18.7 feet. This is deeper. This is shallower. The truss divisions. This is the number of divisions. With the Warren truss, you can see that it's actually going every other. So sometimes if you have an odd number, it won't look particularly even. With a Warren truss, you'll probably want an even number like 14. And it does, this may or may not matter depending on your geometry, but it does start from a low point and then goes to a high point, and then low, then high. If you wanted that zigzag to be reversed, I believe the way you would do it is to set the depth to be negative. There we go. But of course, you have to use this smartly in space. I'm just saying if you wanted the Warren curve to look like, to start from the top and go down, you would want to make the depth negative. But if you have it positive, it's more of like an A rather than a B to start. Howe truss, it's nice. It divides it in half, and Pratt truss is similar to a Howe, but this would change depending on whether your supports are at the top of the truss for a Pratt, or Howe truss, your supports there at the bottom part of the truss, or Brown where you get all of them. Here we're using a little bit of dynamic naming, which I'll go into. I'm just making a list of the top and bottom chords. That's what we're getting from the output. Top and bottom chords are, and these are, I believe they're polylines. Yeah, linear curve. But if you explode it, you can see that it actually is a bunch of segmented curves. As Rob was saying, putting in a single curve at the top and then having all of your diagonals and verticals in the truss, if they're not actually connected at a node, they won't analyze together. You could set it up and your top curve will fly away from the verticals and diagonals, which will just fall into space. So that's a key tenet of finite element modeling, and just make sure your nodes, things are connected at nodes. Even though it looks the same, it may not be the same. So the top and bottom curves are getting broken up and sent into this one list. And then the diagonals are in a second list and the verticals are in another list. This tool called Entwine maintains, it'll flatten items coming into the list, but then maintain everything in those three lists coming out. Oh, I guess I'm not even using this, just to color elements, no matter. So here's that dynamic naming. This will show up in a bunch of scripts later. I find this, it's very useful. It's just a sequence of 3 buttons. First, we're taking a list length, but we're getting the list length of all 3 of the different lists. Then we're creating a series that starts with, well, it starts with 0. I should have made this 1. So, so the list length is 28, 28, 15. So 28 chord members, 28 diagonals, and 15 verticals. Right? And if we look at that, it makes a list that goes from 1 to 28, 1 to 28, and 1 to 15. And then we're going to use the concatenate, which is essentially like that tool before expression, where we could say X and Y, which I believe will do the same thing.
Yeah.
It depends on what you're comfortable with, but I'm giving 3 prefixes for each group: chord, diagonal, vertical. I'm grafting it so that they appear 1 per list, 1 per branch. And that way it'll line up with the series, which are also 1 per branch. And if I concatenate them, now I have a nice list of verticals from 1 to 15, diagonals from 1 to 28, and over here also 1 to 28. And then if I do this X and Y, it looks like it made the exact same thing. So you've got options. Seeing it in that Karumba file was the first time I'd ever seen someone do a concatenate in Grasshopper. I normally just use this, but whatever floats your boat, they both work. I will say that this expression, the longer it gets, the bigger the button gets in your Grasshopper screen. So it's a little hard to control. Whereas this one can be nice and neat, and you can really, it's already doing that. So this one might be a little more compact on your screen. So those are the names. So we're giving, the lines are coming in these 3 branches, 28, 28, 15. The IDs are also coming in 28, 28, 15. And the cross sections, there's 1 per branch. So let me show you, let me go back and show you this. So we've got a material. We are using the cross-section range selector, and then we're using 3 different cross-section selector components to put in this entwined list, which essentially just puts whatever you put in these 3 buttons comes out in 3 branches. I actually want this to be dynamic. So I'm going to double click, do 0 less than 200, which is a quick way to get a number slider that has the values you've put in. And I'm just going to replace these with a little more control. And this one is the chord cross section. This one will be the diagonal. And we're going to make that 20. And then this one is the vertical section. The names, when you change these buttons, are really just for your own sanity. You don't have to name them, but it does help as you're going through a script to rename things as you're doing it. And if you want a little button to appear around a tool or a group of tools, for example, like this, select it, and you do the command is Control-G to group them. And then if you right click in the group space, you can give it a name. So I'm going to say create dynamic names, and then you can just remember what you're doing or group your scripts. You'll notice Nick is probably better at this than I am. I think that's like when I open Nick's scripts, they do seem to be better organized. Okay, so we've got names, we've got beams, we've got 3 different cross sections. The supports we're giving it are the endpoints of the original curve. So you can see the original curve was up here, and since our height, the height is assumed to go down from the curve. You're assumed to be giving it the top chord of the truss, and I think for the most part, that's the way things go. If for some reason it worked the other way, like I said, you would just right click on height and say -X. The truss will be drawn above it, and the supports, again, in our definition here, are being grabbed from the original curve. You can try it both ways. And we're going to give it a load. This one is a point load, and we're giving it a vector. So -Z, and this is 500, -500. This script originated in metric land. So this number was referring to kilonewtons, but because it was wildly out of scale with imperial, I added an extra, I just divided it by 10. And now it's more in the realm of imperial where it works. this is a somewhat tricky idea, but we'll go over it. I want to choose a panel point to put the load at. I don't want to put a load between panel points. I want it to be at a panel point. Looks like there's a question, Nick. Okay, maybe chat to them. So this position of load is choosing, remember on the simple beam where we were choosing a position of load along the beam, and it was actually just evaluating it to the third decimal point. What this is doing is it's taking this 0 to 1 slider, multiplying it by the number of truss divisions. So there's 15 points. It'll end up with 15 points because there's 14 segments. And I want to choose the point that's closest to this position. So it's saying ceiling X times Y minus 1. Actually, it probably should be X. Oh, no, yeah. Plus 1. Because I don't want it to actually choose. I say 0, I want it to actually choose the first one. Yeah. So if I wanted to select every panel point, I would say Y plus 1. But in this case, I actually just want to show, I just want to pick points that are between the start and end points. So I've manipulated this a little bit. I know that there's only 13 points in between, and I don't want the first point to be 0. So I believe that, oh, it does give me this one. Never mind. We'll just, any point is fine. And then what it's going to give me is a number. It's saying 15. And then I'm going to the list. And there are, oh, this will probably give me an error. That's why it was Y minus 1. 0, right? It's giving me an index, which I'm pulling from the vertice point list from the exploded curve. So the output of this truss component gives you top and bottom, diagonals, verticals, but it doesn't really give you points. You can get them from that exploded polyline. And we're saying that that's where I want to put the point load. This is a little different. We want to give the trusses some releases. So I'm using this tool, which is called, I always find it by typing bang, but it's explode tree is what it's called. Control, click, yeah. So it's under Grasshopper set or sets and explode tree. I'm putting it into the names component. Remember, we were using these names before, but I actually only want the branches that refer to diagonals and verticals. I don't want the chords to have any releases because in reality, although they are discrete elements in Karumba and for finite element modeling, in reality, it's probably one long member or maybe one long welded member. You would have instability if everything, well, we could put in some degrees of freedom. And so we're giving the diagonals and verticals a joint by using this beam joint in Karumba. I'm translationally no releases, but rotationally, I've kept, I believe RZ is torsion and it's really not relevant. So I've kept that on. And if you've worked in SAP before, SAP doesn't love it if you release torsion at both ends. So I'm just kind of going by that same principle. Actually, maybe it's this one that's off. We'll see. We will see. All right, so let's do our handy dandy model view. So really quickly, it's giving us it's giving us releases. It's also showing us restraints, and it's showing us where the point load is. I always want to turn on load values so we can see it. Here's our system. So if we move the position of the load, There we go. And then we're linking it up to a simple first order analysis component. There's a little error message here that says a whole bunch of things, but I believe it's actually upset about is that we have a pin support where a member also has a hinge or has a release. So that's something you might see an error for in any other analysis model. Sometimes it's relevant, sometimes it's not, sometimes it's appropriate, but because we have 3 members all coming into one point, we've got a chord, a diagonal, and vertical, which all share a point. 2 of them have releases, 1 of them doesn't, and then the support has some releases as well. That's why we're getting the error. Yeah, exactly. Like if we were to do this, okay, it just wanted one more thing, but you can. Once we turn on the viewer, you'll see that this actually doesn't matter. It still responds appropriately. Let's look at the deflected shape. So the deformation I've turned up really high, but it's not deflecting very much. I mean, we're giving it 10 by 112, 8 by 48, 8 by 10, and we're using a brown truss, which has both diagonals every direction. If I were to do this, oh, now we can see some. Sure. And if I were to increase the load a little bit by, you can see it now deflecting a bit more. Let's try making the sections a little smaller. Let's make the chords a little smaller section, or we could just start from the beginning. See where we get to. And I wonder. Yeah, see, I think that one's not relevant. The direction that we don't want it to rotate in is Y, or that we want to let it rotate in is Y, and that is released. See, if I add another release, it's adding, if I add release X, I believe it's adding it around the endpoints of it. And this is a little hard to see, a little hard to decipher, I would say. Karumba is doing their best. But I think if you just look at the behavior, check these on and off, you can make sure that you're getting the right one. Okay, so we've got the model. And now we're going to look at the results. So these are, suspiciously happy trusses. I'm not saying it's wrong. It's just I'm using the smallest section size for a 100-foot truss.
Pretty deep.
Yeah, it is deep. But see the deflections going further and further in the other direction. I'm going to turn off the model view for a second. We can get. Yes, that was the right one. Build, no numbers. So you can see the moment in the chords themselves. I'm going to turn this on again, but I am not going to show the joints. I just want to be able to see the load moving. So that's kind of interesting. It's a simply supported. I think Rob wants to play with this a bit more, but we have to move on. We have to move on. Are there, the next thing I believe is we can try this. So this to me is dicey. This is an analyzer Karumba component that wants to basically remove, it says true, it only wants compression members to survive, nothing with tension to leave. And if I say false, I'm not sure if that switches to tension. Ideal, it would be nice if it just got rid of zero force members, but it doesn't. It's getting rid of compression and tension members. Yeah, so it doesn't look great because we actually need all those members. But I thought there was a good way to just display. Maybe I could display it without the deformation. Yeah, all right. So this one is, it's false. So only tension members are surviving. If I change that to true, only compression members survive. It's a bit weird. It was, Karumba uses this to demonstrate the tool, but I don't think this is a practical application of the tool. You would never have a truss and then delete half of them. The point is that some of the members take compression, some take tension, and you need both. Okay, we're going to go on to the third. Oh, there's 2 more trusses. And then are we getting into building before lunch? Okay, all right. Well, in that case, I have an hour to do 2 kind of complicated. Well, maybe the thread.
I'd love to see the thread stuff.
Okay. All right. So we're doing parametric truss plus thread. This one will be a little bit different than, it's using some of the basic bones of this script, but we're going to have Karumba optimize, so choose the size for every section. And then we want to record the results in a thread format. So I'm going to go through one by one, just starting with Grasshopper because it may be a little bit more involved than before. So when you open up the file that's just called, it just says a -gh. This is showing how it's going together. I'm using this defined truss type. One thing to notice is I don't have a ton of sliders everywhere. And that's because I know that we are going to be using thread later downstream. And thread, the beauty of it is that you can analyze all different possible combinations of a set of variables at once. But it does have a practical limit where things start to get hairy after about 10,000 different combinations. So I'm trying to limit the choices in order to keep those combinations down. So you'll notice that I've taken out the Warren truss also. So I just have 3 truss types. The length I've specifically, and this is just a tool called value list that's within Grasshopper. Oh, wait. It's called value list. The spacing of the trusses. So this is your tributary width. Obviously, if you're doing a big roof, you might actually know the value, but for the purposes of this study, we don't want to explicitly have a second list of tributary widths that don't make sense with the trusses in their length. So I have a tributary width as a function of length. So it's basically length divided by what? So length divided by 2, length divided by 10. And it's rounding up to the nearest whole number. So that's the tributary width. It's 10. If I do by 2, it's 35. Same thing with depth. So the depth is L over what? So L over 20 will give you a skinnier truss. You can kind of see this visualization here. And the number, and that's a function of length as well. Depth over 6 gives you 12. These are pretty nice, nice numbers. And the load, I want to define it in pounds per square foot. It's just what we're used to. I'm converting to kip per feet. So we're taking the pounds per square foot times the result of the tributary area. So now we have pounds per linear foot. And then we take that divided by 1,000 using the expression. And now we have kips per foot. Another button that I've indicated in pink because it's going to be important later on is spacing. So I want to know what the resulting spacing was, and I want to know what the resulting depth of the truss was. In here, we're just defining the truss itself, taking in these numbers. So the top part is really just putting in numbers, no geometry stuff. We're doing that SDL start length direction. to come up with the bottom chord. Let me turn off this part. So the bottom chord is appearing there. Then I'm moving the top chord up by a certain depth. So we could have used the other truss component where you actually define the depth, but by default, I'm used to this 2 curve one. So that's the one that I went to, but you could have used the other one too. It's asking for number of segments and truss type, which I've just used a little data collector to make the script clean. I'm taking the points at the bottom curve, and these are going to be the support points. And then the support point, the endpoints of the top curve are going to be the out of plane support points. Then I run it through this truss. We're doing the name collector again, except this one, well, it has separate lists. So I could have entwined them here and saved a couple buttons, but we're using the same script that we were doing before. This button is a holdover from when we had worn trusses where we had no verticals. In order to keep from getting an error, I had to have that in there, but since we removed worn, actually don't need it. This is where we're grabbing the curves that form the chords, and they are segmented there. This is where we're getting the curves that form the diagonals and verticals. And I'm just gathering them together in this button called curves. And this other button with the dynamic name. So we've got chord top, chord bottom. You can kind of see CHT, CHB, and then diagonals and verticals. And then this is just a visualization I put in there, but a way to see the other shadow bays at their trib width apart. So as you're making these changes, you get a visual input. You know, they're closer, they're really close, they're very far. You can just see it change in the viewport, but it's just a shadow. Okay, so that's it for the actual grasshoppering. It's mainly, you know, coming in with a plan of all the variable numbers you need to create a truss and have everything associated geometrically with that truss, using the TT button to make a truss, which is essentially just a cluster that I don't want to open. Create names. Here I'm creating names for the chords. Here I'm creating names for the verticals. And then just sort of gathering everything for the next step. I like to make things a group and then right click on it and say blob, and then give it some bright color if it's important and I need it later. We're going to open the next in this series, which is Grasshopper plus Karumba. Okay. So this is a preview of what we're going to get to, which is different section sizes per member using the optimizer. So we've already gone through the creating of the geometry. I'm just going to show the Karumba setup again. We have the points that we're getting from here, the total pins and the out of plane support points. We have our curves from there. So this is, and then we have a load value, a distributed load value that we know we want to use. And we're using gravity. In addition, we've got one support that's just supporting out of plane. Those are the top 2 points. The supports that are fully restrained at the bottom. And we're defining so the lines are coming in 2 different branches of a list. I'll just zoom back here. If you recall, there are 8 different chords and 9 different verticals and diagonals. And then the names list is also the same numbers. So names, IDs, and then the cross section, we are grabbing just the first one on this list. So if we take a moment to look down here, it looks a little bit messy, but this is what I meant by creating your own order of the optimization order. So we're choosing a material, we're choosing a family. We're using this tool called disassemble cross section, which gives you the name, gives you the height. It gives you the area, which is essentially the weight, or at least relative, because the area of the cross section times 490 pounds per cubic foot is the weight per linear foot. It's giving us I in X and Y, which is nice. And then this is a little bit strange, but it is WELY is, if you look at the tooltip, it's the section modulus in the Z direction. Then WPLY is the plastic section modulus. So elastic, plastic, and we have plastic Y positive, or elastic Y positive, plastic Y positive, elastic Z positive, plastic Z positive. These are all values that we like and you might want to sort by. So this is the sort component on steroids. I've changed the input names to match what I'm actually putting into it in order to keep myself sane, because there are too many wires. But I'm asking for a key to sort by, and then all the things that I want to sort with it are the Karumba definition of a cross section, the name, the area, which is also represents weight, the depth, the width, IX, IY, SX, ZX, SY, all this. And I've only set up a simple choice, which is that, are we going to sort the list by weight or by stiffness? So if I choose by stiffness, it's grabbing, this is called stream filter, and it asks for an input, and you can have as many numbers as you want. It just needs to correspond to a number that has a stream. So the input is by stiffness, and you can see in parentheses, it's telling you that right now it's turned to 1. So 1 input stream is going to IYY. Input stream 0 is going into A. And so I can choose how to sort. So really quickly, if we just want to look, this is section sorted by stiffness. This is section sorted by weight. And you can see that the list actually does change. And initially we're assigning every section the first section in the list. And so all of the members that are coming in get that same section. I'm also taking these points, and I think this was a check to see what this tool does, but it's eliminating any duplicate points. And we're also giving the verticals and diagonals a release like we did in the previous script. Then we're assembling the model. We've got our input points that are, it says may or may not be connected by elements. I think they're just saying nodes, somewhat irrelevant if the members are discretized, but doesn't hurt to include them. Input beams and shells in the model. Supports, we've got our one load, which is our uniform live load that's creating a vector from the value we calculated back over here. And running a first order analysis of it.
I think, by the way, I think the points are important to include because there are times when
We're on top.
I think it's important to include the points as in the definition in the model assembly. There are times when supports are defined sort of
Yeah, we're coming up.
it's more, it won't, like when you do meshes, I always see what's problem. I have issues with meshes sometimes. If I don't define those points, it doesn't recognize certain points in the definition, so it doesn't see. So
it doesn't hurt if you include them, but if you find yourself like it's not giving you the result you want because you're trying to put a point in the middle of a mesh or something, try this because that could be what it's asking for. But it's hard to know. Like,
doesn't
hurt, and it can only help, but it may not be necessary. And we're running a first order analysis from it. We're getting our deflection from it, which is here, 84 inches. And I'm running it through the cross-section optimizer. So I ran it first, like as the model as it is. And now the displacement is 4 inches because I said I wanted the maximum utilization to be 0.95. Where did I define that? Oh, up here. Not very clean. And then I actually set up a maximum displacement that changes based on the length of the truss. So truss deflection limits can vary. Sometimes you want a stiffer one, sometimes you can get away with a lighter one, but I don't think it would be any less than L over 175 would be acceptable. So that's you can change it in here, but it's taking the length, which is in feet, multiplying by 12, divided by 175, and then add it as the max displacement. So the max displacement is 4.8, and you can see that what it's actually giving us is 4.72, which is pretty good.
Have you explained the database for the sections themselves?
I think so.
Okay, no, understood. But the only thing is when you can do custom
You can do custom sections.
So if you want to do like US based custom sections, you can actually pull that in. The only
With a Rhino curve, which you could draw in Grasshopper.
yeah, the only no, I'm talking about the actual section strings.
Well, we did talk about how to get how to sort a standard section set by a chosen key.
Yeah, that's
Yeah,
right.
to
Okay.
make your optimization list.
Yeah.
To customize your optimization set.
Yeah.
We talked about that. Yeah. Just catching Rob up, and he's in the room, but he's a busy guy. Okay, so the model, we're disassembling the model, we're disassembling the element, we're disassembling the cross section. So now I can actually see the list of names that it actually chose for every element. And just for fun, I've added that into a nice visualization tool, which is taking, the nice thing about Karumba is whatever order the beams were put in is the order it's going to come out. So here's the beam curves in order, which we're grabbing from our geometry section. And I'm taking the list of names, the list of sections they chose, and I'm using this button called create set. So it's going to create a set of unique names. And then this is a tool called member index. So it's looking for the name of the section per member in the unique set per member. So you can see that there are 17 values, 17 members, but there are only 9 different sections that were chosen, and it's choosing that index. We are putting that into a gradient. So the gradient goes from 0 to the length of the list. So how many unique values are plotted on this chart, and then it's choosing the color per member based on what section it has. That's it. Color members by section, but the manual way. And I'm using another TT tool, which
Heads up, some people might
you might not have
the
this.
sweep component. I apologize.
Mhm.
It might be a proprietary one.
So that's only to view it in 3D like this. But you can turn on this, which is, this is a human tool, I believe, custom preview line weights. So you can preview a line, but you can also give it a thickness. And just because I've made the thickness also dynamic based on the height of the section. So it takes the height of the section and plots that from 1 to 8 line weight and can give you an output of, thinner lines or smaller sections, thicker lines or thicker sections. And I did that because of the frustration I've had with some of these Karumba viewers, not to knock them too hard, but if you say I want to color it by cross section and it doesn't change color, that is, something I'd like to see.
I have to give it the color
Oh, that's right.
back upstream, but don't worry about it now.
Yeah, I'm not going to worry about it now, but yeah, Nick just pointed out it's user error. The reason why the cross section by color doesn't show up is we never gave it a color. I never did. So there we go. Regardless, we've got custom preview line weights per section. So this is pretty cool. We can also turn on our favorite utilization, and we can see that it goes from 8 to 13, depending on the section. Turn that off. Oops. Actually, if you want to turn that on. And the deformation is pretty small. You can see it's still discretizing and splitting up each member to allow us to see the individual deflection, which is cool. And you can still see the utilization on top and bottom of the member section. And Karumba really does draw it with this outline, but it is a little hard to see. It just looks very smooth. It doesn't show the edges. So why do we want to put this into Thread? Thread is a database. How do you want to introduce that? Do we want to jump back and go to Thread? Do we want to skip Thread? I think this is the best example of it.
Thread, let's do Thread. So just,
This is a fixed interest, or you want it, that's what you want.
the next step is Calibri.
Mhm.
I'm saying like.
Oh, the top and bottom. Yeah. So
Restraint.
yeah. So if we were to take this and remove it, it should be totally removed at the top now. I've not restrained it for anything. And if I basically just, now we've got some different results. Oh, this is within itself. Maybe. I expected it to tilt inward more. Something's weird. Okay, Rob always likes to, he likes to play with it.
There's supports there.
There's no, those points are these.
There's no support.
You're seeing a point in the screen because I have it turned on. And then these are the points at the bottom. Let me hide
disconnect
those.
it from the, like, take.
Yeah.
Get rid of that points in up there.
Didn't change.
Hmm.
Yeah,
Well, no time to fix it.
yeah, we'll just leave that. So let's take a break for a second and talk about Thread. Do you have any slides about that?
I don't.
Okay. Can you log in, go to thread.thorntomasetti.com on my account and go, there's a set called like Trust Opti. No, I can't remember, and share it with you so that I can get it. Okay. But you might have some, I might just start opening up your threads and see what we have.
I got nothing.
Red, easiest way to trust is like.
Trust V0.
Nobody knows that.
I don't really do that.
I don't think anyone on the call knows Power BI.
What's it called?
It's going to send you a push. I got to log in and see.
No, I think.
No, I'm trying to log in. I think it's called that one. Yeah.
Other people.
Mhm. I'm trying to log in as Nick on Nick's computer. So Nick has to approve the duo push eventually.
Oh, okay. For here.
Mhm.
Call me. Just call me. I don't do a.
Oh, really? Oh, okay. Call you.
So,
Oh,
I
the
got
push
it.
is really
I
nice.
got a new phone and I haven't.
Okay, so you can see this screen. I'm going to go to Design Explorer. Design. Really quickly, because it has like a nice viewer. It explains the idea really quickly. This is it. This came out of a hackathon years ago. And if you go to TTACM, GitHub, Design Explorer, this website still works. And it's a little simpler. The Thread is just the updated version of this, but this still works. And essentially what it is a data set of, imagine it as rows in Excel where you have all these different variables. In this case, we're looking at a single room in a building and measuring daylight autonomy using Grasshopper and Ladybug to check it. And I believe Mustafa from Ladybug is one of the speakers at AECtech, so you should definitely check it out. Ladybug's a cool tool set, but we're not going to get into that. The purpose of Design Explorer / Thread is to help you do optioneering. So solving a bunch of options and then sorting them afterward and having all those options available as a set. So your inputs, in this case, the inputs were the depth and the height of the louvers, the orientation of the room, the window to wall ratio of the room, and I believe this is solar or something. Then the outputs that they are getting from Ladybug, Honeybee are the cooling kilowatt hours, the heating kilowatt hours, lighting kilowatt hours. What is the effective depth of the louver? So sometimes saying what's the number and orient it to a certain way will give you an effective depth. I'm talking about a data set that I did not create. So if this sounds bogus, I'm doing my best. But generally, the sustainability group is trying to, in this case, tell the architect what are all the different shading options that will get us to daylight autonomy of, from 80 to 100%. So they want to show them the options that will get them there and say, okay, this is orientation from north. So a north facing window, what do we have here? Let's just say that the architects say, well, I really, really want a window wall ratio, no less than 0.5. You can sort this. And now you can see all the different options that will still result in the, so it's basically sorting models by their ending output metrics rather than calculating everything individually. So it takes time to set up a really nice data set, but this is a great example of it. You want to solve a bunch of things at once and sort them later, or you want to create a nice data set and then give the web link to somebody else so that they can view it. So because I'm on,
I just shared it with myself, so you should better search for Trust V0 now, hopefully. Yeah.
There it is. Yeah. Okay. So this is a data set that I ran a couple weeks ago on this Truss Optimizer. You can see this little green button up here. It's loading. But what I did was, it took a long time to run, so I had to let it go overnight. I think it had about 18,000 different threads, which I was informed later exceeds the limit, but it explains why it was so clunky. And because it was so clunky, I don't have the resulting images with it. But essentially what we have now is a live, like truss designer, a live truss designer data set. So we could use this in the exact same way. You could say, I've got, we're designing stadium. The trusses are between 160 and 200. The architect's not quite done yet, but we know that we want them to be as far apart as possible. So maybe L divided by 4 to 2, but we need them to be super, super shallow. Actually, so remember the output of our truss was spacing in feet, because we're not actually calculating the space. We're not actually giving it an explicit spacing. It's a function of the length. So if we say, well, the length of the truss is 160 to 200, and they cannot be closer than 50 because we have to have, I don't know, giant 50-foot sculptures fitting in between or something. And then everyone's going to hit their head if they're not less than 10 feet. And we want the maximum deflection L over X to be as high as possible, because it's very sensitive equipment. So what are our top performers? And as you're sorting this database, we're getting output. We're saying, okay, here's the chord section, and here's the vertical and diagonal section. You can have 14 panel points, a brown truss, 80-foot spacing, 10 feet deep. And this is your pounds per square foot, which is really useful in beginning stages of design when you're trying to come up with tonnage for a stadium roof. What's the tonnage? Let's get a price for it. Pounds per square foot is usually what's used. So creating a pre-solved data set of a bunch of different trusses at different lengths is really useful for that. And now every time I go to this link, I still have this data set available to me. So maybe over the lunch break or as you leave this class, we hope that as you're doing parametric structures, it's not always, parametric structures can be a pretty wide definition. It's not necessarily just, oh, I've hooked up sliders, therefore it's parametric. That's true. But you can also create a data set manually and sort it like this. And I would argue that's also parametric. You're kind of, you got inputs and outputs, and you're making some decisions based on that. But Rhino Grasshopper has some, oh shoot, did I close it?
You still got an instance open.
Oh, it just, sorry, this is, I'm on Nick's computer. Rhino Grasshopper makes it really easy to create that data set. So I'm going to quickly show you that on TT's toolbar. If you have the older version of TT toolbar, it'll look like this. It's called Calibri. And I believe Nick mentioned it in the email that it was going to be something we needed. And I think it's in this plugin folder also. No.
Calibri can be found in the toolbox, but you can also find it from Food for Rhino. You search for Calibri. I believe it was in the email from last night. So it is actually a separate plugin from the TT toolbox at this point.
So I'm just going to quickly, we're not going to run it really. We might just run a couple iterations. But the purpose of this is really just to show you guys how, oh no. Shoot.
Try the download and install. Let's give it a shot.
Sometimes that works, sometimes it doesn't. This is the difference between my computer and Nick's, and they're probably, sometimes it shows you the, we probably don't have time to set this up.
It'd be nice to see it on screen. I can get Calibri really quick.
So you have it, you just don't have the one I'm using.
The old TT toolbox.
Got it. Well, I'll just put the tools where they go. It would be nice to have this run. I think we're going to have an issue with the many trusses on the surface also.
I'll install it.
Okay, but that comes up next. So there are a couple, Calibri only has a couple buttons. One is called iterator, iteration selection, parameters, image setting, and aggregator. So that is going here. This is the 3D app. I love that it actually does kind of show you what's missing. Parameters, I believe, are from here. And then this is the iteration selection. Okay. So I wanted the inputs to be, this is a variable parameter thing. It'll automatically adjust when you put things in. The iterator takes a bunch of different inputs that are sliders or value lists, but they cannot be the human value list. They can't be checkboxes. They can't be a panel. It has to be a slider or a value list that can be easily changed automatically by a computer. So there's some limitations to what can be an input. And in our case, I mean, I did indicate them all with pink. So the input is, or pink or yellow, the input is, let's try to match the order from thread. So we have truss type, length, spacing, depth, panel points, out spacing, out depth. So anything that's in is an iteration, and anything that's out is called a parameter. Let's just go back to that. So help me remember: truss, length, spacing, depth, and panel points. So there's 5 inputs. So I've got truss type, I've got length in feet, I've got spacing as a function of feet, as length, function of length, depth, and panel points. So these are all indicated in yellow. Those are inputs. Those are variables. And what's cool is see how it says that there are total 18,000 different possible combinations. You can use this button, which is called iteration selection. It's creating a domain. And I'm just saying 1 to 100, give me just the first 100 combinations. If you actually press this button, it'll cycle through all 100. Might take a couple minutes, so I'm going to say 1 to 25. Might go fast. So if you press this button fly, it'll say you've got 5 inputs connected and we're running 26 iterations. Do you want to continue? This is a nice feature they have, because if you accidentally press fly and it starts doing 18,000, it may lock up your computer for a little bit. So you can see that it's working. I can't really change the zoom, but it'll automatically cycle through all of those combos. And you can see how fast Karumba is giving the results.
That was at 25.
That was it. And then this is called parameters. So this is where you're collecting all the outputs, which I have indicated in pink. So I want to know out, I want to know spacing, depth, chord section, vertical and diagonal section, the weight per square foot, the max DCR, the max deflection, and then the deflection as a function of length. That's a lot.
Maybe just hit the first 4.
Yeah.
Out spacing,
So spacing is out, depth is out,
cross section.
cross section of chords and
Yeah.
Okay, so chord section.
Yeah.
Here.
Chord section.
In this, you know, they're giving us different ones. So you can see there's a different chord at the bottom. I'm just grabbing the largest one, the heaviest one. Vertical diagonal section. What else do we have? Looks like we've got structure PSF. Is that-
WT, PSF,
Mhm.
max DCR, max depth.
Max DCR is over here. Max deflection,
And then LX.
deflection. Yeah. So these are all the results that we want to calculate. I think the strength of Colibri and running through these iterations, if you can reduce the amount of inputs, you could have as many outputs as you want. So if you know, the fewer options you give it initially, the faster it'll run, the more likely you can actually get it up online in a nice, usable, viewable format. And you're not punished at all for having, you could have 1 million of these and you won't be punished. You'll be punished for the number of iterations. But what's nice is it'll actually show you the output of each thing. So if I say fly, watch this change. There it goes. It's running through a bunch of different options and combinations. And then the last tool is really just Colibri wants to record it. And I'm probably not going to show this part because I don't want to bog down Nick's computer, but it asks for a whole folder where it's going to dump images, and it's also going to jump. So it's going to ask for genome, which is this, the inputs. Phenome is parameters. This part's always a little confusing. It takes me a second to remember which is which, but it does. If you hover over the tooltip, it'll say iterator. This says parameters. Then it wants to know image setting. I wanted to give it a, oh, that's this tool.
Front view, yeah.
So I want it to be the front view in Rhino, and I want it to save as this. And then I, you know, some generic widths and heights, 600. This can be a little hard because, especially if you're changing the geometry a lot, sometimes that truss will be out of view, but whatever. It's still, it's representative. And if you have something nice and colorful, it'll show you, it'll give you enough visual cues. And if I were to say write, so this is actually asking for a folder. Maybe I'll just
put the domain down to like 5 and let's try.
Okay. Select a directory. So
Yep.
Under desktop, I'm going to make a new folder called AEC. Whatever. Okay, that's it. AEC. That's where it's going to write. It goes really fast. 10. I want to have something in there.
CSV.
Yeah. So we're going to write it. We're going to change that to true
Looks like something's what's an orange with an orange wire going
into this.
okay.
Oh, the image setting. I forgot to put in. There we go. I think that's it. No. Oh yeah, it's the old image setting, right? Let's for desktop AC.
Oh, true false. Do you actually have to run it?
I think you have to run. Oh no, it needs the folder. Right. That part's missing too. So I'm going to give it this file path to folder. And that should have written, aha. So the first thing you see is data.csv. So it's formatting all of the input and output data into a CSV that you can upload to Thread, or honestly Design Explorer. They still read it. Like, so in order to access Thread, if you're a TT employee, you can use your employee login. If you're a non-TT employee, you just have to make an account with the core apps. But this is free and open to everybody.
Everybody in this class should have
Everybody in this
access to
class.
Thread. We've taken your emails and added you to the whitelist.
Okay, yeah. Everyone in the class should have access with your email that you use to sign up. Okay, so I'm just going to move this over here so that we can really see what's happening as it goes. So I'm going to set the iterator to run, and it's going to be simultaneously creating visual image files in this folder, and it's going to be writing data into the CSV. So it says this is where, and you notice that when I press that button, a txt file shows up. It says running.txt. If you accidentally press go and it starts to run, there are two ways to stop the iterator. You can press escape, so it says here, but you kind of have to keep pressing it because you have to get it in a moment where it's between iterations. So the timing of the escape button has to be right, or you just have to delete this file in the folder and that'll stop the run. However, depending on what you're naming the file, sometimes that running folder can get lost in the middle of your JPEGs, and just something to keep in note. So I said go, and look, it's already boom, 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 boom. Deleted, yeah, okay, whatever. We've got images. So brown, I forgot what it's called, 1044. Oh no, it's so small. Let's get a longer one, maybe this one. Yeah. So you can play with the image, get a test till it's right, but the smaller the image, the better. Trust me. When you want to upload it to Thread, do you want to try?
Yeah, let's give it a shot.
Okay. Let me just redo it with a better picture.
We did have one question from the chat, which I'll throw out here now while Aloy's on it. From Kuroki. I guess the opti cross-section is defined by max utility and max displacement. Does the algorithm consider combination among movement, axial force, and shear?
Let's look at the button for a second.
I think no.
I think no. I think no.
It's only taking account of displacement and utility. I think what the key here is, if you want to get access to those values, you need to decompose the element. So the cross-section optimizer is not taking account of them, as far as we know.
Yeah. That's where you can be kind of, the hack for it is to spend time creating your list. You can also, using all of these values and using this expression component, you can do math here in Grasshopper. You can figure out the shear capacity of each of these. You can figure out the critical buckling load, because you know the length. It's parametric, but you'll know the length, and you can figure out anything that you want in order for it to be sorted. So I guess optimizing for shear would be sorting by shear capacity, perhaps. Like that could be one way to do it. Right now we're only doing weight and stiffness, but and actually I grabbed weight. I think when I'm saying capture the front view, I think it really does. It starts at, so I had in my viewport, I had the truss all the way over here because I was looking at Grasshopper at the same time.
It does start from here.
So if you put it in the center and then we open Grasshopper again, it should write the images a little nicer. It'll ask you, oh, okay. True to write. Yes, I want to override everything in the folder. And I want to go. And you can see it running in the background. There. Okay, so now we've got some better ones. Let's see if the image looks, okay, that's nice. So now we will go to thread. And you'll want to create a new project. And we're going to say AECtech cross test project. Within the project, you can have multiple data sets, but you cannot have multiple data sets that have different inputs and outputs. Like the format needs to be the same. So you can have, we could have a data set in here where we run it where the optimization list is sorted by weight. And then we could have another data set where the optimization list is sorted by stiffness, but you can't have a data set of, I don't know, the simple cantilever beam displacements and trusses in the same project.
Columns are gonna match.
The columns need to match. And then furthermore, you can't take a data set, delete the data, rename it, re-upload new data with columns, just create a new data set. If there's something about the legacy that if you try to take one data set and change it to a different one, it won't work. So we're going to say 1 to 10. You know, these are runs 1 to 10. This is another way you could break up a big data set is you could say, I'm going to run all the Pratt trusses in one set or all the Howe trusses in one set. And then combining them, you could get up to your, you get over the 10,000 limit, but any individual data set should not really be more than 10,000. So it wants a CSV, which we're going to drag. And then it's saying, okay, here are the columns, the ins and outs. This all looks right. You can add a little more flavor description if you want, but I think it's pretty self-explanatory. And then we want to manage the associated support files. So we're going to drag in these JPEGs. It looks like it made some 3D images, which I've never. Is that what this is?
No, it's just the numbering. 40, 50. They're not 3D.
No, they're JSON. Isn't that a 3D?
Oh, it's just a format. Could be anything. Could be strings. Could be 3D model.
All right. So now we've uploaded everything. That's under the entries point. And then we can do this drop down and go to entries. And you can see here's all the data that came through. If someone gives you access to their data set, you can actually download it as a CSV, which is cool. You can edit it manually once it's in this format. You can also append it with multiple runs. So, and then in the dashboard, it's pretty blank. You don't automatically get that nice visualization, but play around with a small data set and some of these widgets. Obviously, my favorite is parallel coordinates, which is what I used to from Design Explorer. You size it. You can press this button that has the little wheels to change the title of the widget. I just delete it. It's pretty obvious what's happening. And you can unselect things that you don't want. So the thread rating is a way to take some of these options and give them top scores and then be able to come back to them later. And in this case, I'm not doing that. Don't care. So I'm unchecking. I want to label the axes. And okay, that's good. And then to preview it, you would press this button that says exit edit mode. It's a little scary. It's right by delete. So just be careful. But you can kind of get a glimpse of what you're looking at. It wants to know, what do you want to color it by? I think it's nice to color by weight per square foot. That's kind of cool. You can see that the weight per square foot is lowest when it's blue, which is interesting. I mean, brown trusses, you can see they're the stiffest, but that since they have the double number of diagonals, they're bound to be heavier than the other types. If we want to go back to the images, yeah. Sorry, I forgot about the images. So image tiles, that's the one we want. And if we want to set up like Design Explorer, we want to put it down here, give it a ton of room. We can also have the data table just shows it as a tabular format, which is what I was showing before. Again, I don't really need a name for this, and the thread tags are off already. Now, if you said, I know my truss is 50 feet long, and I think you can also sort. Oh, ascending, descending. Yes, so you can see that there. And I want the weight per square foot to be as low as possible. It seems like these are pretty similar. You can see this little number that pops up is the value that you're selecting. If I were to say sort by length, that changes, or color by length, it changes this little tag. So if you know, if you got 50 foot length, it looks like they didn't get to the option of choosing panel points or spacings because we only gave it 10 iterations to solve for. But you just said, oh, no, we definitely want to use, this looks like it's using 14s and 12s, and this is using 10s and 10s. These are using the same section size. So what is this option? And you can click on it and get all the information from it. So
I did send Nick a,
okay, Rob is sending me a file. What's it called?
State of
cut
it.
one.
Refresh.
So Rob may be following along, and he made his own truss, which we're going to try to pull up. Maybe.
You shared it with me? You shared the data?
Yeah,
I'm going to catch up on chats.
I think we're good.
Okay.
Besides the cross section, and then everyone was pointing out your folder was disconnected.
okay, check it now.
But that was, I've connected it now.
Yeah, refresh.
Thanks, Andrew.
Just analysis one.
Okay. So which one? Data set.
11,000.
Swarm demo has no entries. Oops. This has no entries.
All right, pull down the report. This is similar.
Okay, so here's, I want to color by weight per foot. So this is actually taking Karumba's output and making really nice images from it. Yeah, this is nice. And then it looks like for real, the weight per square foot is 149, or weight per linear foot. Okay, that makes more sense. And then it has output, largest beam profile. So this is someone else's version of what we just did. So have a think about the way you work. And if there's a data set you feel like you're constantly referencing, you can definitely pre-solve everything and then have it up for you whenever you need it. This one idea that we had about this was that it could be something you pull up in a meeting with architects. You could show them, here are your options. If you know it's coming, you can pre-solve it. So at this point, I think we're going to do the many trusses option, which Nick is going to show. And
We're at break.
oh, we're at break time.
Yeah, I think we might break. And we'll discuss how much we did in the afternoon.
Okay. Yeah. All right. So we're going to take a break for lunch. We've got quite a bit in the afternoon. How is everybody feeling? If you have an opinion about whether it's moving too slow, too fast, let us know during the break. Otherwise, we're going to try to make it fast, because we're going to try to make it fast unless we get a lot of requests otherwise, because we just have a lot of cool stuff to show you guys.
All right, hour for lunch. We'll be back at 2 o'clock. If anybody wants to send any messages in the hour break, just feel free. We'll be around.
We're going to leave this, the meeting open. We'll
Yes.
just mute ourselves and we'll just mute ourselves. Yeah.
That's it.
Camera off to it.
Yes. Okay, so the read and write will be slightly different. That is true. Let's have a quick look down here. So read is only going to need to know the file path. And then the output will basically be formatted into columns or rows depending on what you want to see. So yes, they are going to have different formats. Obviously, there's nothing that comes out of this component because we're writing. And there are a series of write options, which can be quite useful to plug into here. Things like, should I automatically overwrite the file? Should I close and save Excel after you've written the data? All can be quite useful.
Do you have the newest TT toolbox, T3? Okay. I think they have they've
The
written
newer
it,
version?
the newer version. It looks different, slightly different inputs is what they're saying.
Okay.
I just said as long as it works.
It's quite possible my components are a little different to yours. Apologies. Here's that it works. And I might just, so I will say the reason I set this to a high resolution is because it takes quite a long time to solve. You can see that this is almost a full second or half a second to solve. And if I bump this down to, let's say, a resolution of, say, 2 feet, it's going to take even longer to solve, but we'll get a more accurate tributary area measurement out of the. All right, you can see that we've got now square edges on our corners. Things are looking much cleaner. There's still a little bit of shaking here, but it's within range for the schematic design sort of level. Okay, the next example I'm going to open is going to leverage reading information from Excel. So that one was involved writing information to Excel. This next one is going to show you how you can read information from Excel. We've got a new separate Rhino file, reasonably simple, just a series of curves. The example I'm trying to describe here is the creation of a loading diagram. This is where engineers will sketch in a plan view approximate regions over a floor plate which have varying loading capacities. So, you know, an auditorium with a bunch of people is going to have more loading than the hallway next to it, as an example, right? So these diagrams are generally created by engineers by hand. They're sketching shapes and then applying hatches to it. This script is going to demonstrate how we might be able to create that diagram automatically from an Excel document. So the Rhino file includes a series of layers. Layers 1, 2, 3, and 4. Those are the names of the layers. These are going to be relevant for us to be aware of. The name of the layer is going to relate to an Excel object, which I'm about to open up right now. So in that folder I've provided, you should also have a single Excel document as part of the full building, parametric loading. So let's open this and have a quick look at it. So this is a sort of a passed down version of a loading diagram chart we had from a team in the New York office. They had names for the areas, they had different functions, floor slab constructions, and most critically, the total live load and total dead load. Our goal in this script is to tie directly the name, number 1, of the area to the layers that are present in the Rhino model. So every curve on layer 1 in the Rhino model is considered to have loading of theater, lower seating, 250 pounds per square foot, let's say. And we're going to read our Excel sheet and apply this loading to the curves in Rhino automatically. That's our goal here. So the script is going to leverage the fact that these layers are present already. In this case, you'll see that we've got 2 little parts going on. The portion at the bottom, this leverages the Human Tools dynamic geometry pipeline. What it lets us do is reference all of the curves that are present on the layers that are present in Rhino. So I want you to grab from layer 1, 2, 3, and 4, all of the curves that are present. As an output of this component, we get a data tree, which is basically all the curves that are on that layer. So branch 0 is all the curves on layer 1, branch 1 is all the curves on layer 2, etc., etc. So we've referenced in the curves. Fantastic. Here are our curve objects. What we need to do now is we need to open an Excel spreadsheet, import the data, and then find a matching object from the Rhino model. So the first step, we're going to use the read Excel component. Again, I apologize, my components may look a little different to your TT toolbox, but all we're really looking to apply here is a path to a file. So this is going to be the parametric loading XLS that I said previously. And then when we click true, We're going to read that information, and it's going to be output as a data tree. So if we have a look at the direct results, you'll see that a lot of these cells are empty to begin with, and the information we want tends to start after branch 6. So all I'm doing here is getting rid of all the empty cells and getting all the information that's relevant to what we want. So you can see this is exactly reading the Excel spreadsheet. We've got 1 theater seating, the name of the floor slab, and the total live load, dead load, as read directly from this document. And the next portion here involves a matching approach, very similar to what Aloy showed earlier, using set components and the ability to find a member within a set. So our goal, first of all, is to take the information that's being read directly from Excel, which includes the name, 1, and the loading, 3. Extract, first of all, the load ID. So the item index 0 is going to be the name of the loading we want to apply. You can see I'm making a set from these objects, which gives us 1, 2, 3, and 4. And then when reading the layers from the Rhino model, I'm also bringing across the names that we got. So I understand that there are a number of curves, 1, 1, 1, 1, that have the property 1. Our component here, member index, lets us search item 1, 2, 3, 4, and find which index from this list matches the member we're asking for. So at the end of the day, what we get is an understanding from the Excel spreadsheet, which of the column, well, so which of the rows are relevant to the name of the layer inside of Rhino. The next little chunk here is simply allowing us to create a data tag from that information. But the critical thing is the step at the end where we're doing some visualization. So at this point, we know for every curve in the Rhino model, what loading type it is in the spreadsheet. It's either 250, it's 50, it's 100, or it's 480. Which is what this component has now given for us, a name of the loading value. At the end here, we have a little color spectrum creation. So creating data in Grasshopper is the first step, but actually visualizing it is just as important. What we're doing here is taking all of the closed curves from the Rhino model, and we're going to build a surface from them. We're then going to apply a color spectrum to those surfaces based on their loading value, which we have here. So all of the potential loading values per surface are defined here, 250, 600, etc. And then we want to create a range. So we want to create a range from the lowest value in the spreadsheet, 100, up to the highest value in the spreadsheet, 600. We're going to run that through our color spectrum component, which is going to say that all the low values should be bluish and all the high values should be reddish. The ones in the middle are going to be yellowish. And we're going to use a custom preview component to apply to the surfaces the color we want. Let's turn this on. And there we go. So what we're seeing here is that the areas that have a high load are being shown in red. The areas that have a low load are being shown in blue. Or am I got it reversed?
No, you're right. I just noticed that component going into the gradient, which I didn't recognize.
First and last.
It's a tree sloth
And
component.
people don't have it.
Yeah, maybe. Because I just tried to open it and it gave me an error, and I'm like, that must be what that is.
Okay, Aloy has pointed out that I've got on my canvas here one more component that may not have loaded when you loaded the script. I apologize. This is a really useful set of tools called Tree Sloth. This component here grabs the first item and the last item from any list. Super useful. That can be found on Food for Rhino. Use it all the time. Obviously, you could also just grab the zeroth and the reverse,
which is what I did in a different script. But
okay, so the goal here is that this is all live and parametric, right? If we were to change the outline of the curve, right? If in Rhino for some reason we needed to change the shape of the loading diagram, we can just grab this curve, we can move this corner across, and it's still going to read the color, and it's still going to apply the color no matter what we do to the curves inherent. So parametrically, we can change the shapes here. And then if we wanted to, we could actually put in new values in the Excel. If we save this document, the script would reread the Excel document and apply the new loading. The last little chunk I've included down here essentially leverages some more human tools. I'm taking the same approach, but in this case, I'm not using color to define the regions. I'm using a hatch pattern. So human has a great set of tools here called the, where's this guy? Create hatch. Allows you to take any closed region and draw a hatch based on the existing hatches in the file. And this is probably closer to what you would see in a, you know, a loading diagram view. Obviously not all stacked up like this. And separately, I've also included in this tag. So basically taking all the information from the Excel spreadsheet. I'm just going to put a clipping plane in here. So make this a little bit. Get this out of the way. We zoom in and enable our tag here. We're now also tagging the regions based on the information being read from the Excel spreadsheet. So at this point, we've got a, just enable the parametric loading diagram where we can change the shape of the curve. Our hatches will, oh, that's the wrong curve. The red one. Our hatches will update continuously. So reasonably simple idea. The key trick here is the matching, being able to find a match from one data set, which is the Excel spreadsheet, to the curves, which you have in Rhino. And this is all being done through the layers matching the name of the area.
It's like a VLOOKUP.
Exactly. This is a lookup table with Excel being the basis and Grasshopper doing the looking. Any questions there? Simple stuff, no analysis really involved, but just pointing out that you don't always have to do analysis to have benefits from Grasshopper. This is more about being able to adapt and adjust without reworking things over and over.
And working with the traditional tools that engineers use.
Yeah,
Start every project.
we're using just this very basic data set from Excel, but you can see that any information can be brought in from Excel, and through a little bit of trickery in terms of matching, etc., you can start making it useful to the objects in the Rhino file. So
Sent you some screenshots in Slack.
it's not a, it's a two-way process, is what I would say. It's always going to be a little bit of, you know, using it in two directions. Oh, okay. So quick example, unnamed project, hopefully. This was an example where we actually did the same thing you just saw just there. We had a very, very complicated loading diagram for a very, very big site, and the same process was applied. And in this case, the results were actually uploaded to Mirar, which is our 3D online visualizer. So we've got sort of a live 3D loading diagram capable out of all those same tools. Bunch in the chat. I'm just going to assume. All right, cool. All right, I'm going to turn it back over to Aloy for our next example.
I think we're gonna pop back and
Deployable,
forth.
yep. And then, yeah, I jump back.
Ron's here too. Okay, so we've just swapped places across the table, and we're going to, I think the scripts I have should work in this file, but I'm just going to open the one that I know they work in. So the next file we're going to look at is called Deployable Building Results Critical Load Case. Oh, there's nothing in there. Is it in the Google Drive? Did I forget to move it?
Deployable sim, keep going.
Yeah, but nothing's in there. Just give me a second. I think I know where it is on my computer.
You may just drop it back into the drive.
Yeah. Where's 7? We changed the names a bunch of times. You know when it's uploaded? Okay, so we've got a couple different files and I'm going to download all of them. Okay. Now we're in business. And we're going to open the Rhino file number 1, input surfaces as shell. I just use this for a lot of different things. I know at least the units should work. And we'll start by building this model. But first I'm going to show a couple slides to introduce what this problem that we're trying to solve even is and how we're going to approach it. So it's a different way to optimize. So obviously in Karumba, you can optimize cross sections, but there's a way to optimize, or at least help find something within Grasshopper that already exists. It's called Galapagos. You guys may be familiar with it. So we are going to go over how to create a fitness function and then run it. And what does it mean? So before we were doing stuff in Thread, we were using Galapagos a lot. And an example of where you might need it, example we're going to think about, which is a very structural engineer's question, which is if you have a ton of different loading, if you have you know, a program with no program, Hudson Yards, for example, the shed is a building that has no program, but every program. And the roof design needs to be able to accommodate lighting, sound equipment, sculptures, who knows what. It's probably very over-designed, but an engineer's worst fear is if you were to miss a potential combination of loads that somehow is worse than the one that seems obvious. Another case of that would be positions of cars on a bridge. This is actually a Karumba example. We're not going to do it today, but you can grab it from their website. If you type in Karumba examples, it'll show basically a truck on a bridge, and it tries to find the worst case for moment or worst case for deflection. I think in that case, they should be the same, or worst case for reactions. So how to solve for the worst case, especially if you have multiple different inputs. This is kind of the project practical example we're using. If you Google flyover Iceland or Canada, you'll find pictures like this. This is essentially like a interactive movie theater. The picture on the right is showing all these people watching a movie on a curved 3D screen. And while they're watching the movie, usually it's something expansive, like flying over. These images are actual shots from the theater. Drone video over Antarctica, for example. While you're watching the movie, the gondola that's holding a bunch of people is deployed. It shakes, it turns, it tilts, it does a bunch of stuff, and then it comes back in. And so we've got a series of 9 deployments. However, you can see some gondolas don't have any people in it, like this one or that one. And when they're not deployed, they don't go out. So the simple question is the worst case the case where all of them are deployed, or could there possibly be a worst case where a combination of some of them is worse than all of them? And if you've done any work with permutations and combinations, you know that this could get really, really hairy. When you have 9 objects where there are no repetitions of the 9 keys, and the order of the keys doesn't matter, that's still, I think it's 526 different possible combinations of deployments where if only one gondola is deployed, you've got 9 different options. If all 9 are deployed, you only have 1 different option. There's a nice inverse thing going on there. The number of combinations for 4 and 5 are the same. And the number of combinations for 8 and 1 are also the same, because it's like, which one is not deployed? But what makes this a little hairy is the practical example I'm using is the engineer of the gondolas themselves have 577 different load cases per movement type. So you take 577 times 526. Now you've got millions of over 1 million combinations, I believe, if you include all the different factored load combinations you might want to put those things in. So it gets hairy really fast. We want to maybe save the SAP model from running through thousands of combinations and just figure out which ones do we need to look at using Rhino Grasshopper. So simply, I'm building this geometry in Rhino using, this is just the tilt. I'm just creating a plane with a tilt here. You can see it's perfectly vertical. Now it's at 30, just to make it a little interesting. The size of the grid, I'm saying X and Y is 20 by 12, number of grids 4 by 4, but just to match, I think, well, you can definitely change it. You can make it more complicated. Obviously, the more grids you make, the more combinations you'll get. And I'll show you this a little bit down here. This gets very hairy very quickly. So this is simply a lunchbox component. So you might not have this. I realize I forgot. I rely on lunchbox kind of a lot. It just makes a grid, and this gives you a 2D grid with cells. And what's nice about that is each individual cell is a closed polyline. So if you've ever, making a grid is pretty easy, but then sorting them into closed loops without splitting a surface or something can be a little, takes a lot of buttons, and Lunchbox just does it for you. So we're taking advantage of that. There's also a slider for the depth of the structure, pretty self-explanatory. And then we're doing a quick test here where I'm measuring the start point of every, I'm using this tool called Evaluate Curve at the start point of every curve. The reason why I want this and not any other get point on curve tool is because it gives you a tangent vector. And I want to use that to compare to A to B. So the A vector is the tangent vector upon which the plane is created, the tilted plane. And then compare it to the vector of every curve. And I'm just saying if it equals 0, 1, or no. And that way I'm separating the vertical members, or at least the ones that are angled with the plane from the horizontal members. I believe downstream, I'm not really giving them any different treatment, but say X is, I did see it captured a random one there. It's less than 0.1. Vertical members, yeah, for some reason it's not getting the one in the end. I wonder why. Okay. Well, for some reason it's not getting the one on the end, and I'm not entirely sure why. But that's something I could troubleshoot later. Other things that we know we need to build the system are the points themselves that are causing these offset loads. For the purpose of the demonstration, we're just going to deal with point loads. So I've created because these are, they give you individual cells. You can get the centroid of the cell. So see, the first item is this rectangle down here. You can get the centroid of the cell with this button, which is called area. Sometimes I want the area. Most of the time I use this tool to get the centroid. And I'm saying that wow, I guess I'm going to use Nick's new tool, middle mouse on the tool, then that. That is much nicer. So I'm calling those the stay points, like they're staying, they're not being deployed. Then I'm taking all the points and moving them out by a distance that is a variable, but I'm not really I imagine if this were a real scenario, the amount of distance it's going out is not actually a variable. And then these I'm calling the out points. So it's the points that are out, we got the points that are in. And now we just have to figure out which ones to grab from each list. This component down here is just taking all the points from the grid. This tool is removing duplicates. We're using deconstruct point to grab the Z coordinate. I'm creating a set, or without creating set from it, I know I'm looking for ones that are on, that have Z coordinate of 0. And it's just giving me, I'm searching for 0 in the list of coordinates and then returning the points that meet that criteria. So here are our support points. Now this is where it gets a little tricky, and there's a little bit of funny grasshoppering in here. So before you tell me, once you open up the script and you tell me you're not actually calculating all the possible combinations, I know it was breaking the script. And it wasn't getting fun. Once it gets too real, then sometimes it's not as fun anymore. I think the idea is enough to get you guys started. So that's how we're doing it. And the way I'm setting it up is getting a list of the number of points. So this is getting a list of cells. So it should be 16. And 16 there. I'm generating an alphabetical list based on that. There's a reason why I didn't stick to numbers, and I can't remember now, but I think it'll come up later. So you can, this is create a character sequence. It'll always go in the order of the alphabet, and it's a bit funny, this thing, to control it. This tool is just creating a series, and I want to create the number deployed. So it goes from 1 to 15. And there are some combinations. This basically will tell you how many different combinations should be as a result of this number within the total number and the chosen number. You can just, that's the equation for combinations without repetitions or without the order mattering. So that's something that I just had to spend some time Googling. There is an equation for this. And I'm just using that to say, I want a bunch of different values, possible values from this. Well, I'm using this tool called random reduce. So it's totally random, and it's generating, this tool is used to generate a bunch of different numbers that will serve to be the seed for the randomness. Now, this is where I've broken from being strict about actually calculating the combinations, and I'm just letting Grasshopper do something fun. Because if you've had any experience with the Grasshopper random tools, it's a bit funny. Some numbers give you the exact same result. Some seeds, yeah, some seeds give you the exact same result. So I may not be hitting every possible combination of 4 deployments with this, but it's going to be close enough for our demonstration. And then I'm sorting those combos by name, and I'm joining them, and I'm removing anything that was, so I'm sorting all the different, here, I'll just show you what it looks like. So because it's reducing the list of characters, you end up with a bunch of lists like this. And when I say I want to sort them alphabetically, it's because I want to make sure that I'm getting rid of any duplicate combinations. So I'm sorting them alphabetically. You can see they kind of change, joining them. and then creating a set from them. So the set will call out any combos that are the same sequence of letters. So I'm going from 1820 to 1147. I mean, it reduced some, there were some duplicates in there. And then this would determine which deployment we use. And you can see that when I try to click on this, this is actually the item selector from the human component, human tools. The more options you have going in it, see how it's thinking, the longer it takes to even display what it's doing. So
Over 1,000, right, is what it's trying to display now.
yeah, it's trying to display over 1,000. So I hope it stops soon. Stop. Because you can see below it, I've just given up trying to use that as any sort of option. And I'm just using the list item.
400.
Yeah. So I'm choosing item 409. We're only going to test one at a time with Karumba. Hopefully this.
See the slider is you here.
And the slider is actually the variable, not this. Also, Galapagos or Thread will not accept this blue item dropdown because it's a human component. It's not a native Grasshopper one. Okay. All right. So we're just going to ignore that. So the deployment that was chosen was 409 and it's FJOP. And I'm splitting this combination up again into the 4 things and searching for those 4 items in the set of all the letters, then returning the indices. And I'm doing 2 things. I'm grabbing those indices from the out points and I'm calling those indices from the in points. So now I have a set of 16 points where 4 of them are out in this deployment. And if I were to choose any other combination, you'd see them moving in and out to meet those letters. That part's pretty simple. It's kind of fun. That's where Grasshopper gets fun. And I'm going to say that all of these points get some sort of load. You know, the gondola weighs something, but it doesn't weigh as much as when there are people on it. This is getting so this is getting the actual points. And this is getting the cell of the member. And that's because we need, structurally, we can't just have a load out there. Well, you could have it calculate a moment and put that moment back on the in point, but I think we want to see stuff. We're doing Grasshopper, we're doing animations after all. So I'm just grabbing the cell that those points came from and drawing 4 members out to that out point, just so we can see it. We can see it moving in and out. So those points are in, these are the points that are out. Regardless of whether it's in or out, it still knows what cell it belongs to. So it seems like probably the hardest part is coming up with the combinations, but the Grasshopper part, as you can see, is pretty easy. So we're going to move on to adding Karumba. Well, you can see the results very quickly. So I'm going to go through this quick. A lot of this we've seen before. We've got our support points. I'm putting a point load on. So the load points were still in those 2 branches. The first branch are the in points. And so those are getting 1 kip. The out points are getting 5 kips. Then we also have gravity going on, and that's going to be working against us with the slant of the building. And we have the connection members, which I'm just giving as pretty small pipes. The actual horizontal members and vertical members are getting W sections, which we're applying as a line to beam. So here's where I'm using the collector because we've got 3 different groups. It's just nice to make it look a little cleaner. We're adding joints to the connection sticks that go out. So they're allowed to rotate. And we're assembling all of that stuff in the model. In the model view, we can see the deformation is turned up to 4. But I can make it 0. I could make it 9. Looks like there might be a question in the chat.
Yeah.
I'll get to it later. Or is it any, can
It's
I answer
the
it
load
now?
combination.
Oh, thank you. We'll get to that in form finding. But yes, remind me again, load combo workaround. So we've assembled the model. in this tool, and actually I probably should have put it before here. Go. Deformation. Oh, that's strange. You see that, Nick?
Again, the deformation you set to 0, it wouldn't deform at all. Run, yeah, put the run model in there, and then
Let's see how it's not actually moving.
elements.
Oh, it has to go there. That's what it is. Woo. Okay, too much deformation. So you can see it's responding really quickly, and it's nice that the point loads are on and they're following the movement. We can also see that there's a dead load there too. So just for fun, we're using this get utilization of beams, but as you recall, we had a little bit of discrepancy between the utilization that comes out here and the legend. You can use this handy tool called bounds to just grab the start and end of a group of numbers. So this is saying 0.04, so that's 4% to 160. And this is 174 to 172. You know, it's kind of close. It's probably enough that thinking ahead, we might want to run a check that finds the worst case for utilization. We might want to run a check that finds the worst case for reaction forces. We might want to run a case that finds the worst case for total displacement. Basically, you want to think ahead to what are you going to need to test for? And that's our Karumba assembly, which should seem familiar. And now we're going to add the Galapagos portion to it.
Maybe 2 seconds on what Galapagos.
Mhm. So Galapagos is an evolutionary solver within Rhino Grasshopper, and it takes in a bunch of variables and it solves for one thing, which is called the fitness function, and then gives you that combination of variables that gives you the fitness function and the goal. There's only two options. You can maximize that number or you can minimize the number. We'll get into it. So for example, I found this picture on the internet. This is ranking a bunch of, do you want to?
Oh, go ahead.
Ranking a bunch of different turtles by, I'm guessing, their fighting power. You can see 20%, 60%, 70%. Seems to be a little bit backwards, but and then their smarts, their brain power, and then maybe this is their speed. I'm not sure. And in the end, that's giving you a blended number. And this is, it's just in a nutshell represents what we try to do with fitness functions. You can only give Galapagos one number, but if you have multiple goals, you have to add them together to create one number. You can add them together straight, but it does seem to work better if you give multiple goals different averages. I'm not going to get into the multiple goals part. Nick will in his script after this, but so we're just going to solve for one thing, and we're going to choose which, we're going to have a choice which thing to solve for at one time. But what you do is you'll put it into the Galapagos button, and it will, I'll show you in a second, but the genomes are all the different sliders that you can change that give you a result that you're trying to solve for. And the fitness is a single number. Within Galapagos, there's two different solvers. This button on the left that looks like a pink seed with like hairs growing out of it.
It's a sperm and egg.
Oh.
Yeah.
It's called an, whatever. It's evolutionary solver. So the way that works generally, I'm not an expert on this, but the way I understand it is it tries a couple options, and if one group of combinations seems to be more influential or better than the previous one, it just starts to go in that direction. So it tries to learn from the previous iteration and go in that direction. The green button is called the annealing solver, and that is more like thread in that it'll just brute force everything in a somewhat random fashion and try to give you the results afterward. Okay, so we've got the Galapagos. So Galapagos is here. It's just this button. It's pink. It has embryos, eggs, eyes. I always thought those were eyes.
I think there are two cells.
I thought they were just really derpy eyeballs.
Might be worth showing how to connect the Galapagos.
Yeah. So the connecting the wires, right now, the only genome, you know, I'm trying to cut down on the number of things it can choose. So we can get crazy once we run this a little bit if we want to connect the actual number deployed as a variable. But right now, to connect it, you have to drag it from Galapagos to the object, and then it snaps. So when you select the Galapagos object, it should very easily, very nicely show you what it's actually pulling from. So the only variable I'm checking is the deployment, which combination of ins and outs gondolas are, which combination are we actually testing through Karumba? So if I choose, I only want 6 to come out, then all these deployments only have 6. So right now the number is not a variable, but it could be. You can attach this genome to as many sliders as you want, but see, it won't snap to the human component. Just fine. And then the fitness is, I'm setting up a little test in Karumba using the filter, which I mentioned before. It can take any number of inputs and outputs, but depending on what number is given, it'll let certain streams through. This is a value list that I just typed up. It's a Grasshopper tool. So I said, worst case DCR 0, worst case displacement 1, worst case reaction 2. So input stream 0 is coming from this beam utilization results component, where I'm grabbing the bounds. Then I'm using this tool called deconstruct domain. So that is a Grasshopper native tool, very useful. And it gives you the start and end point. So the end is the highest domain. And I'm going to say that that's the worst case DCR of all the members on this structure. So I'm going to put that into input stream 1. Input stream 2 is, let me remind myself, worst case displacement. But where do we get that? We're getting it from here. The model's already giving it to you. And I'm putting that in input stream 2 or input stream 1. And then worst case reaction, I'm using this. And I'm making some executive decisions here, but you know, whatever you're trying to find for your model, it can be unique for that check. But the reactions are given in XYZ. I'm just summing them together, or I'm using this deconstruct point tool to split up that vector into 3 points. You could also use split vector. They actually seem to work interchangeably. And then I'm creating a vector from the 3 solely to get this, which is length. I want to know the total length, the resultant vector. You could use math. You could split this up into 3 parts and do a Pythagorean theorem, but this tool works good. This tool works well to just give you the length. I'm getting the min and max with the bounds tool, and then I'm grabbing the highest total reaction. And then from Grasshopper, I'm dragging the fitness into this. So whatever metric I would like to be the thing to check for, reaction, displacement, or DCR, it's one number going into Galapagos. And actually, I think, yeah, we'll see. I mean, I was expecting something different from when I actually ran this. So, but because I'm trying to find the worst case, I want to maximize that fitness function. So basically, I'm already taking the worst displacement from the model, the worst reaction from the model, the worst, what was the third one? Displacement, reaction, forgot, DCR. I want to maximize that. And because that'll give me the load case where that thing is the worst. Now, a lot of times, a lot of Galapagos files, and you'll probably see that with Nix later, is it'll say what combination of these things is the best, which combination reduces the deflection. So a lot of times you can design that way, but I really wanted to show this example of a case where you might want to maximize that fitness function. So you double click on Galapagos to open it. You see this, where that's where you choose min, max. Then you choose the solvers. I guess we'll try one versus the other. These three buttons over here, this says do not display any genomes in the Rhino viewport. This says only display genomes that have superseded previous genomes as being better. When they say genomes, they just mean clicks along the sliders and any iteration of that you've created. And this is display every single genome that they're testing in the Rhino viewport. I like to see it, but it's computationally heavy. It goes a lot faster if you don't choose to look at it, but because this is a class, we want to look. So I'm starting it and see it's just running through. The only genome is which deployment it's using. And you can see Karumba is responding pretty quickly as well with moments. Oh, I've turned on moments just because it's fun to see. But you kind of have to let it go a little bit.
Generates a starting population.
Nick says it generates a starting population. Those are the dots that you see. And then they take, the best 10, and then they go in the direction of the best 10. The thing is, because we're doing a lot of random stuff, the conclusion I've come to doing this is that the randomness of it is actually makes Galapagos struggle. Like it's hard for it needs more steps to actually come up to a conclusion. Needs a little bit more variables to get there. So what I've noticed, what you should see in the shape of Galapagos is a very wide strip here. And then it should get narrower and narrower and narrower towards the top. But I've run this a couple times and it never gets narrower, which tells me that it's struggling to, the randomness is it's hard for it to learn from that. Does that make sense?
Yeah.
It's unusual.
So like you could maybe switch to minimize, like that might be enough to have it. I know you're trying to find worst case.
Yeah. I think we need another variable in there, probably the number of deployments or something.
Something besides the
Something that's directly responsible and not random.
All of this is to say that using Galapagos can be tricky to set up the problem statement correctly, to kind of focus in on the things you're trying to get to. I think from a sort of learning point of view, the goal of showing you Galapagos is just a different way to iterate through sliders, right? So the thread report we showed earlier is basically the same thing as we're doing here, right? We were just focusing down on the options that gave us the best results. In that case, the user was defining the best results by choosing parallel coordinates in thread. In this case, we are defining the goal in Grasshopper. So the maximize or minimize based on the results from the Karumba analysis.
And you're only going to end up with one. If you let it run long enough, it'll just either converge, or you just have to stop it after a while. You see it's not really changing. You end up with one combination.
And that one combination you might use as your starting worst case, right? The goal here is just to allow Galapagos to test and make some choices for you. It would be impossible to, iterate through all these sliders manually and make informed decisions from them.
Yeah. Yeah, there were 1,000 of them. I mean, there are a number of different ways we could do it. Like we could brute force solve and thread for all of these things. We could solve it in Karumba, write it all to Excel and filter it there. But if you just need a quick answer, but you think that the formula is always going to be the same, like it's always going to be, this combination, but maybe the grid is bigger. So the reason why I'm using the example of that flyover theater is that they are building them all over. And the formula is pretty much the same. There's 9 gondolas. There's maybe 9, maybe 16, like they could do more, but a lot of, if you know that some things are fixed, but every instance is different enough that you might need to find a new worst case if the structure was different in each iteration. But anyway, so it doesn't seem to solve, like it doesn't seem to actually find a result, is what I was noticing. So this looks very unusual compared to other Galapagos things that I've tried. So in a way, we built this whole script to find the worst case and we can't even find it. I think the other issue might be the seed, the fact that it's using the random seed, and some of those sliders give you the same output. I did think that maybe, you know, with DCR, it was giving me that, with displacement, it's giving us that, perhaps with reaction would be different, but I think this is enough to show you what you could do, and we know where we need to improve, but trying to make the script do everything is probably too much for the short time that we have on this. So at this time, we are going to jump to shells, which is a very exciting big change between sticks and shells. So I just, for the engineers in the room, this may be old news, but a beam and a truss and a shell are all related. Their behavior is similar. You'll remember that when we were studying the single beam, if you fix it for rotation at the ends, you would end up with a shape like this, where the tension and compression flip towards the ends. That indicates a fixed end condition. Same with a truss. If, you know, in this case, the truss is supported along the bottom edge, so you've got compression at the top, tension at the bottom, but it's not fully tensioned. If we were to move this point to the center line of the truss, it would end up looking more like this simple span beam with compression at the top and tension on the bottom. But I just wanted to show, this is a simple Karumba example that you can find on their example page, but we did a couple things. Of course, we couldn't just take their example as is, and we tweaked it a bit. So this is giving us it's a shell that's of a certain length. We're just referencing that in. We're giving it that says the heights, it's in centimeters, but technically it's inches. We gave it a name. This is, these are the different, okay, so cross-section assignment is similar to beams, except that you just choose shell instead of I section or O or whatever. And there are variables and other such things, but really shell constant, if you have a single surface, is what you need. We're giving it a name, gave it a mesh. We're asking for some points. This is really just showing the points along the top, I believe. Then this is the part where we're adding some variability into it, is how do we want to support it and how quickly can it react? So I'm testing between having supports at the either end, which is what's shown here, supports at the midline, or supports at the lowest Z coordinates. And this is set up in the same way we did the other Grasshopper script, where you have a value list that has 0, 1, 2, and then you have a bunch of inputs, and then it only releases the one that you've chosen as the supports. We also have gravity, and we have a bunch of point loads. So this one's bringing it in 0, but there's a toggle that Karumba put in. So if I toggle it to true, those loads now are going sideways. So this is, in a way, kind of simulating a very long shear wall. But I'm just trying to show the different ways that a shell can be modeled. We've assembled the model the way we've done before. We've got our load, support, and the element, which is simply the mesh for the shell. We're using a first order analysis, and it's telling us the displacement. We're using the model view component to show deformation, which is minimal. You can see it barely moving there. Yeah, so you can see it is moving, but not much. The reactions are on, but I guess the values are somewhat hidden because we're showing everything all together. In this case, we're showing principal stress 1 as our color scale, and you can see it still has CT, but we could say utilization. That gives you, utilization and principal stress 1, or did I have it on 2? 1 or 2? 1. So you can see, I believe this is position of results. So this is pretty subtle, but you know when you're looking at a shell, do you want to look at the stress in the top part of the shell, the bottom part, or the midline of the shell? The midline usually sometimes has no forces. It's the neutral axis of the shell. It's through the thickness rather than, so just like a beam, it has a neutral axis. Displacement, that's pretty simple. Utilization, 1, 2, and then von Mises, which gives you the combination. It's almost like a resultant stress. Typically, we only look at this for ductile materials and nothing brittle, but it gives us a prettier diagram here. So I'm breaking my own rule for the moment. And this, I should have said, this component is called shell view. So it looks so similar to beam view. The only difference is that it's taking a shell. You don't have the option to look at moment or shear or axial force the way we did with beams. This is also a new tool where we're grabbing. The reason why we included the points this time is because we want to be able to draw stress lines from them. And so we're taking all the points in the mesh. And one thing to note is this is called mesh a surface, and we're having UV counts. It's 20 versus 20, and that's, I wonder if we make this a little bit bigger. Hard to tell what's U and V. Then we have maybe more regular grid points. You can see the mesh grid. So all those points, we are grabbing them later on down here. Once you've created the mesh element, take the points out and make sure that those are, they're part of the system because we're adding them. Actually, no, they're not part of the system. We're using that to actually call them out and find live load points in a different case. But you can call them later down here. This number of the pattern, I'm not really sure where that comes from. It was, I think, to just try to reduce the amount so that less curves, I think. Yeah, that's all I don't think there's a real reason for that. This tool is called Shell Line Results, and it can show you force flow. We can, I shouldn't have done that. Force flow works for me sometimes. I'll say that. It's pretty cool.
3D.
No, I think it should work on a shell, but it needs something different than this. That's what we're giving it. Not all the points. Uh-oh. So these are all the points. Change it to what? Oh yeah, force flow. No, it wants something else. Force direction, sources. Oh wait. So I think this is why I went away from this for this demonstration. I was like, oh. Yeah, I mean, principal stress is good. And it's nice because it gives you lines in 1 and 2 directions. This is a Grasshopper native component called just color, RGB. And so, and it goes from 250. So A is the alpha channel, that's transparency, and then RGB is the colors. So this is blue is getting full, the full 250, R is getting the full 250. And then we're putting those colors. It's the same thing as a swatch, but the Karumba example people have defined it. It's old school, so maybe it existed before the swatch. Wow. So we put in all the points. That's what that looks like. So that must have been why they reduced it. And that can be a really useful diagram if you have if you've got an unusually shaped shell and you just want to see, it gives you a lot of, the word I'm looking for is maybe,
It's pure compression, pure tension.
yeah, pure compression, pure tension in this scenario. It can see if it's, you can see right away if something looks right or if it's behaving differently.
So is the form geometric?
The length of the beam and.
No,
the
it's not.
loading.
Well, it's a reference thing in Rhino. But so yeah, right now we've got the ends fully fixed, but if we choose the midline at the ends, it should look like that. And that looks more like, you know, what we're used to seeing. If you connect a beam at the center line, at the neutral axis, you've got compression on top, tension on the bottom.
Yeah,
But-
it's just a simple beam.
Yeah.
Yes, that's the whole point. Rob has reiterated shells and beams.
If you have the aspect of surface was more of a
Square.
1-to-1 or a 2-to-1, they would form an arch.
It would be different, but we're trying to reiterate that shells and beams and trusses all follow the same principle, and the location of the supports
Is the-
matters. Yeah. So at either end, fully fixed, you get this reversal. At the midline, it stays pretty much the same. And Rob is saying if we were to take this surface, we get some pretty funky different results here. Yeah.
Parabola-ish.
Ish. Like a parabola. Oh.
Like striking
That's it.
high.
Mhm. Lowest Z. This is a compression load for a freestanding, basically a wall on the ground. We're getting some points there. But if we choose that down here, their option of putting in lateral load.
We're getting shear wall territory.
Yeah.
At this point.
So that's how we can relate a shell to a beam or a wall. But I'm going to take a break here and switch with Nick again, because we're getting into how to use a shell and how, well, I would say this is the way Rob uses Karumba most of the time, is we get a strange shape from the architect before we've panelized it with trusses or beams. You can take a look at what it's doing as just a mass.
Yeah.
See if it's unbalanced, see if it like wants to tip over. You can make some pretty quick decisions with a blob before you start to get into the structural. The simpler, the better at these early stages. So.
Hello again, everybody. Okay. All right, next in the list, we're going to look at the define cross-section heights from moments. This one actually does not require a Rhino file. Let's just leave the units in feet and open up the Grasshopper file. Okay, I've got a couple of different versions of the script here. Again, just trying to work through complexity. Let's start with the cross-section height from moment 01. I'm just going to hide the stuff that's HIDE under selection, guys. And what we want to look at here, or we want to zoom to, is this small grid that we've created. I'm just going to talk about how we've generated this grid and some of the variable inputs we're going to use in the script. So there's one defined input here, which is a point. This point could be put anywhere. You know, we could have a separate point anywhere else we like. All that's being used to generate is the base point to generate a grid. This one is actually found inside the standard Grasshopper toolbox. So this is similar to the lunchbox tool but it's found up under vertices and grid up the top there. Takes as an input a point, which is the base plane, and then we're simply defining the number of cells of the grid in one extent or the other, and the size of the cell. So currently the size of the cell is 1 foot. That's pretty small. Let's maybe bump that up to a 6 foot or so module here. So 6 foot as our size is going to bump our grid up significantly. And again, we're all parametric here. So if we were to change the number of instances in this axis or that axis, we're going to get a larger or smaller base surface. The problem here, the problem we're trying to get to is let's call it a roof canopy where we have a series of supports beneath. And we want to define the cross-section height of this member based on some of the loading we're getting as a result from Karumba. So essentially you can imagine, deeper beams where we have more moment, or beams maybe in the other axis where we require it. So we've generated ourselves a grid. We're going to take that grid and we're going to break it into a series of line segments. So at this point, we've got all of 1,100 or so line segments. If you want to, you can also turn on this little component, which is giving us some dimensions here. So we're at about 126 feet for a canopy by about 84 feet for a canopy. This is a really nice little component. Again, this is display, dimensions, and linear dimension. And in this case, it just requires you to give a point for display. Using a bounding box to find the edges, and then just grabbing the edge vertices from that bounding box. So the starting inputs here are a grid of points, sorry, a grid of curves. And then additionally, we want to create a series of supports that are placed at intersects between these objects. So this portion down below is leveraging something called the MD slider object. And what this basically allows us to do is create a variable input that's assuming a bounds of 0 to 1 in each of these axes. So similar to the parameterization of a curve that Aloy was talking about a little earlier, if we were to move this point around, we're essentially defining a new parameter value or 2 coordinates for a point. So you can see we've got 4 of them here. And what this results in at the end of the day is a selection from the original list of points of the point that's sort of closest to this domain. So you can sort of imagine these graphically, these little panels here. Were I to start moving this object around, I'm going to be moving the point that I'm choosing from our original list. So obviously down the very far corner would be a point at the very edge of our grid. And if we move it across, we've got a different position. So all of this is being used to define the support positions for our roof. And obviously if we move these around, we're going to see a change in the structural results. All right, so 4 inputs define 4 points, which give us 4 support positions. The other thing we're building here is a mesh from the points, which we'll use for Karumba. So our inputs here are a list of curves, which are the segments of our structure, and a list of support points for those objects. So this is the parametric part of our script, the stuff that can change. I'll open up O2 now, which is the inclusion of Karumba as part of that script. And I guess I'll just bump my cell size up as well to 6 feet for this. Results. Get rid of that for the time. All right. So at the end, we've got some Karumba stuff happening. I'm going to just disable this for the time being and talk through the Karumba setup. So similar to what we've seen before today, we're going to take our list of lines and we're going to remove any duplicates from here. So this is relevant because we've got cells of curves. There are 1,100 or 1,200 unique lines. Once we look for duplicates, we're down to 635. So any edge that was duplicated between 2 cells has been gotten rid of. Classic line to beam, and in this case, we're using that same process of assigning a unique name to every beam through concatenation. So beam is the prefix, and then create a series of numbers, concat them together, you get beam 0 through beam 600. So the rest of our setup is going to involve applying a load, and this load is going to be a mesh load. So we are actually regenerating a mesh from our list of points. Zoom. And that's what's going to be loaded as far as Karumba is concerned. We're going to take that mesh and apply a uniform load to it. So we've got our z-axis. It's going to be related to gravity. It's pointing down. Type of load is going to be mesh constant, and we've got point loads. In this case, we're leaving the orientation local to the mesh, not global. All right, classic place our supports, and then this is going to be drawn from our variable input. So our supports here can move were we to move the positional coordinate of this variable, right? So we're essentially defining new support positions by moving these 4 panels around. All right, supports defined, loads defined, objects defined, collect the model together. And model run. So we're getting displacements out of this already of 88 feet, which is rather large, but we'll just go with it.
Inches.
Oh, 88 inches. Sorry, you're right. Yes. So whenever you see centimeters here, should have noticed that. So whenever you see centimeters, you assume inches. You see meters, you assume feet.
Except in the cross sections where centimeter,
It's a bit different.
it's millimeter.
All right, let's have a look in this case at our beam view, which in this case, because we're treating all of our elements as curves, right, that's why we're using the beam view. So we're loading the model as a mesh, but we're actually analyzing the model as beam elements, individual unique beam elements. Yeah, you're right. All right. So I'm just going to preview off the mesh here, and we're going to start to see that we're getting individual results basically for every segment that's part of our input objects. And so the intention here is to take the results that we're getting from the Karumba component and use them to generate a geometry, which is what we're getting at the very end here. So the results component is going to give us 2 useful things. Obviously, it's going to give us, the visualization of the forces. We can turn on the moment, etc. We can start to see stresses and displacement, just like we were seeing with the mesh objects. But most critically, what it gives us here, in addition to the legend component, is it'll actually give us some geometry. And this geometry is the default, well, it depends on what you're asking for. In this case, I've got the mx as the checked parameter in the section forces. What this means is that the curves I get out are going to be related to mx. If I switch over the type of section force I'm looking for from this component, you'll notice that the curve is displaced in a different method, right? So mx versus my is going to give us a different output. In this case, what I'm going to leave on is the my component. You can see basically wherever the support is being placed, in this case, we're getting a peak in the my. There's a larger region around that position. Okay, so taking the output of that component, and I may just use the beam view to increase displacement here. Results, model view. Take our model, bring the display scales right down. All right, start to see what's going on here. All right, so we'll get rid of the loads and supports here, leave the joints off. All right, so at this point, when we control the deformation, we're also controlling, or at least looking to control, the amplitude of those outputs. You can see as we get the deformation goes higher, we're getting more difference between the original position and the deformed curve. This little chunk at the end here is designed to take the original list of curves, which are flat and are on the ground, or in a defined XY plane, and find their analogy or the analogous curve in the displaced difference. So essentially what we're looking to define is the difference between this curve and its displaced version of the curve. And we're going to use that delta to define a height for the section of that element. So the grasshopper chunk here is grab the endpoints of the original position of the original curve, these two endpoints. At the same time, grab the endpoints of the displaced curve. We're going to project these to the plane. We're going to measure the difference in their height. At the end of the day, we're going to get a bounds, which is telling us what the minimum and maximum displacement is between those two curves. So at the end here, we get min and max values. This is going to be used to move the original points. So all we're doing here is taking the start and end points of the original curve and moving them up or down in the z-axis based on the amplitude of the resultant analysis curve here. So where these curves are above the section plane, we're going to be extruding up. Where these curves are below it, we're going to be extruding down. And at the end of the day, we're creating a 4-point surface from those results. So you can see here, basically what we get are the 2 points of the original curve, the 2 points of the displaced curve, and a surface generated between those two. So giving us deeper moments at the positions where the columns would be. I'm just going to preview this off. We'll preview this on at the end. So here is our system. We've got 4 column positions, and you can see we're getting much deeper sections at the positions of the columns. And again, were we to adjust any of the variable inputs upstream, for example, changing the position of a column in the corner, we're going to start to see those sections change as the column position moves around. This is somewhat arbitrary, as I am defining the amount of depth based on the deformation. So, greater deformation here is going to eat a greater section property, give you a greater section property.
You did give it a domain.
I will, yeah. So at this little portion down here, there is a chunk that is remapping parameters. So a very useful component here essentially allows you to take a set of values and apply them to a new domain. So what this is saying is that I'm positive I don't want any section heights less than 0.02, and I don't want any section heights larger than 1, which will basically mean if those values do exist in the mapping from the Karumba output, it'll remap them so that they are now between the bounds that we have defined.
The note about units, I think this actually is in meters. Don't think about it too hard.
What, the geometry itself?
Well, we used the Karumba examples as a good basis, and they were made in metric, and especially that one.
Yeah.
It was giving me all sorts of issues. I was like, I think it actually is a meter. Like it's actually, yeah, we got to bake and measure it.
So yeah, that's, we are leveraging this deformation scale as well, sort of leveraging this against the fact that we're defining a upper and lower bounds. So we're sort of, we're playing at the edges here. We're not really trying to zoom down in on an exact result.
You could set up any scaled comparison of any output from Karumba in the same way. So if you just took like the moment, then it would never change regardless of the deformation scale. But what we want to show you is that you can take any output from Karumba and put it back in.
Exactly. And so, I'm using the MX in this case. Let's see what it looked like if we, the MY. What if we use the MX, right? We don't get as much variation. Let's try.
But I mean, if you actually took beam output, it wouldn't vary if you changed the definition.
That's true,
That's
right? So the key here is that I'm leveraging this curve output, but Alternatively, I could use the, decompose element.
Yeah.
Oh, yeah,
Because
yeah.
you're going to here. Let's do that, but. Oh,
You don't get it.
Oh,
All right,
'cause
so
you
you
have
don't get a
MV.
deformed curve.
yeah, do MY. If you switch whether it's going into the view versus the analysis, I think it.
So yeah, if you don't want to see any deformation, right, just leave this model view off and assume you're getting outputs that are not deformed, right? There's no deformation
Right.
in that result. Okay, to keep the ball rolling, there's some questions in there. So
Oh.
I should be paying attention to. Might be old questions.
They're old.
Okay, cool. Keep the ball rolling here. We're going to move on to our next example.
Actually, can you show it? People were asking about the mesh from points.
Oh yeah, okay.
It's native Grasshopper,
This
but
guy.
if you could just do that thing.
Yep.
Yeah, there it is.
It's up
So it's
under mesh utilities. It's taking a list of points, and the tricky part here is basically we want to have the U and V dimensions. They need to be relative to the size of the grid that we're making.
Mhm.
So basically 15 and 20 would be, I think this is divided by 2, would be my guess. Plus 1.
Plus one, because there's
Oh.
always one extra point.
Because there's one extra indice in the list.
Mhm.
So the U and V dimensions are relative to this plus 1, so 16 and 21. It takes a flat list of points and just wants U and V dimensions, as I said, relative to upstream.
So all I was saying in the chat was like, if you have a random list, this won't work.
Yeah, this is quite hard to work with, to be honest, this mesh from points, because you have to know the input structure. You have to know U and V coordinates, and it will break unless you get them right.
Yeah.
But yeah, a quick way to get from points to a mesh. Okay, next example is going to involve a Rhino file and a Grasshopper file. We're moving on to play with column positions.
We've got an hour left. We could go through 4.5 minutes.
Right, so this is more similar to let's say an architectural problem, right? We have some predefined inputs inside of our Rhino environment, and we're going to build a Grasshopper Karumba script that allows us to test different things from this model. So I'm going to play with column positions, and I'm going to open one. We may not look at the Octopus version just today for expediency. Okay. So what we have is a canopy surface. We have two buildings that are beneath the canopy surface, and we've got a curve on the ground. What we have here is basically the curve on the ground represents place where a column could land. So a column to hold up this canopy is allowed to land anywhere inside this curve, which means it cannot land outside the curve and it cannot land inside the box. The boxes are areas where columns cannot land. And our goal here is to take this input surface. We're going to, on that surface, create a series of points. We're doing that through a lovely little Galapagos component here, which can be quite useful. Aloy showed previously allowing you to attach Galapagos to multiple, what's it called, phenomes, which are basically number sliders. But what Galapagos comes pre-packaged with, right? So you can attach Galapagos to one of these. Galapagos has this component called the gene pool. And what this lets you do is set up a series of sliders that you can send Galapagos to only edit, right? So instead of having to copy paste multiple sliders, have Galapagos point at all of these, I can use the gene pool to find a fixed number of parameters with a range that I define. So they do have to have the same range. They kind of variable ranges in here. But in this case, what we're doing is we're saying, place a point on the surface between 0 and 1 as a domain. And what it's going to do is place a series of, I think, 10 or 15 points in this case. So 16 points on the roof, 16 points on the ground. So what we get here is a series of 16 points. If I was to alter this number, you can see we're putting the column top in a different potential position. So these are all just potential column tops as far as our solver is concerned. And just a different way to get to it than having multiple sliders together. So that places a point on the surface. We're going to do a little bit of work here to get those points also on the ground. So we're taking the points on the surface and we're doing a closest point. So any point on the surface, I want you to pull it down and I want you to place that point on a surface that is defined by the curve on the ground. So you can see here, none of these points are allowed to land outside of that green region. And to add to it a little bit, you can see here that we've removed a little bit of the domain, 0.5, so that the points can't go to the very edge. If I put this all the way up at 1, you can see that that is not at the very edge of the surface. There is some variance there in what the edge is considered. All right, so this little script eventually draws us some columns. Those columns are currently reasonably randomly defined. All they have as a variable is you can land on the surface and you can land on this area. That's it, right? We're generating a series of columns. Those columns are going to change position were we to change the inputs, right? So wherever this moves around to, a new column is going to be placed. Our goal is to measure the displacement with Karumba of this canopy based on the column positions, and then minimize displacement by varying the column positions. So let the columns go where they want to minimize the displacement of this roof. So the parametric part is just the setup, setting up the allowable variable positions of these objects. The fact that we're using a curve and making a surface is what prevents them from ever getting outside of that region. All right, this is a really great utility that Karumba comes pre-packaged with. This is the Karumba mesher. Once you start getting into shells, as Rob said earlier, if you're doing finite element, everything has to be connected and adjacent, coincident, clean is what we're saying here. And what this mesh component allows us to do is take any input surface from Rhino and then generate a mesh from it. Most critically, it allows us to add specific points as part of that mesh. So you can see here what we're saying is the column tops, wherever the column tops are, I have to make sure that there is a node that is part of the mesh that is coincident with that position. So essentially you can't have nodes in the middle of the cell in this case. It would have to be always at the position on the edge. You also have a mesh resolution control here, which I'm just going to set to 10 feet for the time being. You may want to bump this down once we get going. The output is a mesh, and this mesh includes inherently a node at the position of the column top, right? So our setup here is a mesh, a series of curves beneath it, whereby we can constrain or we can adjust the position of those columns. That's the setup for our script.
The base boundary tool.
Oh yeah, so this guy here, really useful for investigating meshes. If you don't have this turned on, you're trying to preview a mesh, it'll usually just give you this sort of green surface, I guess. And what we're really interested in here is making sure that our nodes are coincident with mesh edges. So I'm using mesh boundary faces here. It's up on the mesh tool, analysis, just to graphically confirm that, you know, we're getting nodes at the column tops. All right, so our inputs for the Karumba portion, as well as the Galapagos portion, are going to be the mesh. This is the thing we're going to load and give properties to. We've got our support points on the ground, which are going to be the positions that are supported as far as Karumba is concerned. And we've got the sticks that make up the column objects that are part of this. So those are the inputs. I'm going to open up the O2 version of this. So we've got what we saw previously, all the inputs as we saw. We've got our, just preview this off. We've got our mesh. All right, the Karumba portion, we're using a shell cross section in this case. So a little bit different. We're using the mesh to shell. So our input for the mesh to shell is our mesh that we created. Defining a cross-section here through a shell constant and a domain of heights. So basically what this is defining is a series of shell thicknesses. You don't have to have just one input for the height of a shell. You can use a domain, in this case, 6 to 24, step 10 times, which means I've got 6 inches, 7.8, all the way up to 24 inches as a possible shell thickness for this object. All right, so down below, we're going to set up the column portion. So we're going to take the column objects that we've built. We're going to define some cross sections for these. This is just using a pipe section. Same thing, setting up a domain of thicknesses that are potentially available for it and giving the name via the concatenation we're used to. So in this case, we're doing radius as the prefix and R5 is the name of the object based on its size. Using the joint definition here, and in this case, all of the B objects, which I believe are
To the right. Yeah.
to the right.
Mm.
Yeah, there it is. Which are our columns. I wish that was C personally, but are going to receive those releases at start and end. Okay, so we've got shell constant property. We're going to have a gravity load on this, so we could do a mesh load to just start with gravity. Supports for our points at the bottom, properties for our curves. We are assembling our model, and on the output, we are getting a displacement value in inches, right? So this might be a case we want to have a look at shell view. And turn off all our upstream things, including the surface. A little bit strange looking.
The position of the results, if you do,
0.
no, if you do 0, it'll be, if you go to either end, it should be more.
0.5.
What?
We don't want these to be.
Oh, like 1, like all the way to one end or the other, I think.
Yeah.
So if you have the shell thickness,
Oh, it's
the
putting it up
neutral
in there.
axis is in the center, and then I think it's 1 and -1. So you're going to get the most extreme results at either end. If you look at the position, the 1 versus -1 should give you the most extreme, I believe.
Yeah.
That's what that's doing.
Well, our intention here is to essentially do a little bit of Galapagos, like we were talking about previously. So we're just going to leverage the displacement in this case. And our goal is going to be to reduce or minimize the amount of displacement based on variable column positions. So I'll just turn on our column positions. All right, so our genome in this case, as I said, is 2 variables. And it's nice that we're using this gene pool because you see we only need 2 wires basically to get up to 16 genes each time. So it's kind of a lot faster than going through a multiple slider. Our fitness is basically taking the displacement value and making sure we grab the smallest value from that list.
You're grabbing the large.
Reversed. Yes. Agreed. But the thing is, there's only one item from this list.
Yeah, but you want to minimize the maximum.
True. True.
So the reverse is, it's getting the maximum displaced point. Because the minimum is 0. So if you say you want to minimize the minimum, there's going to be one point that's 0 and it won't change anything. Yeah, the reverse the list item. And then should work.
That's gonna be
Yeah.
minimized. Yeah.
And you want to minimize the maximum.
Yeah. All right. So genome's plugged in, fitness is plugged in. Whip open Galapagos. We're going to be minimizing here. We like to see it dance around as much as we can. So we're going to display all genomes in the viewport. I'm just going to use the evolutionary solver here and we'll click OK.
Wait, start.
Oh, you're right. Sorry. Start. Not OK.
It's been a long day.
It has been a long day. Okay. Start solver. Oh, and I didn't put. All right. Let's stop solver. So I'm going to
You can
display,
change that.
you can,
Mhm.
all genomes and start solving. And so you can see what's happening here, right? Our column position variables are being allowed to dance around. I want to test as many different options as I can. Each time we are storing the resultant displacement from that run. And the goal is, once we let it run a bunch of times, to start to identify the column positions that give us the minimum displacement. So again, this is something we could have technically probably set up as a thread report, using displacement as the goal, or the sort of one of the output columns in this case.
Galapagos listener. So
As in, oh, just listen to the results. So yeah,
it has a recorder, which then you could finagle into thread format.
I was going to show that actually. So Aloy just brought up an interesting point here, right? So Galapagos is solving these iterations and then storing the data itself, right? We are not storing the result of the Karumba run as part of this sort of tool. There's no reason that we can't, is what I was going to get to here. And you can see that we've actually already started to, you can see that Galapagos is pretty sure that it wants the columns around about these positions, or it's struggling to move them into new positions to give a smaller displacement. And if I start to see this happening where I'm not getting much variation in the changes here, this is when I would stop the solver and I would try and reinstate the iteration that gave us the minimum displacement, right? So at this point, these sliders are at the positions that give the minimum displacement, which sort of makes sense. You know, some columns at this end, some columns at that end, and some columns in the middle.
You had a question about where the supports were defined. So are they at the bottom of the columns or at the top of the columns?
Supports in this case are defined at the bottom of the column. So the bottom of the column here is the support point. And the assumption is that Karumba, because they're coincident with the curve, and the top of the column is coincident with the mesh, that the forces are all going to be transferred through those edges down to the base.
Oh, he says their degree of freedom isn't, nothing's clicked on it.
Ah,
But I think we defined it as a support. Remember we were having that, the other
I still
thing
don't get these.
somehow it is saying it's doing something.
I know, without any buttons
Nothing.
toggled.
Yeah. Yeah, good point. Good catch. Oh, that did change.
Yeah. Fair enough.
Hmm.
So there's one more example here I'm probably going to skip over, but again, this was a case where we can use Galapagos because we have a single variable, right, to optimize for. We didn't do any weighted averages here. We just looked for displacement and we tried to minimize that. I do have one more example. I won't spend any time talking about it here because it does require one plugin you may not have. Octopus is a similar approach to optimization. Even has a pretty pink button, looks like this. Its tool set is up here, looking like that. You might not have it here, but what this is trying to do is multivariable optimization. So not just one variable. In this case, the Galapagos script is trying to look at the mass of the model as well as the displacement, and in this case, a geometric parameter. What happens if our columns intersect one of the boxes below? Obviously, we don't want that. That column would not be viable. And that's what the Galapagos, that's what the Octopus script is looking to get to. But we do only have 45 minutes left, and there's a bunch of cool form finding stuff coming. So I'm going to.
Can you just show, so there was a question about, and this is a good one. Maybe we can just touch on it quickly. The question was, if you give Galapagos the same initial conditions, will it give the same results? So I typed in that if it's more likely with the evolutionary solver to get different results with the same inputs, it's less likely to happen with annealing. However, in the evolutionary, you can reinstate a genome to make sure that that doesn't happen. Can you just show that?
Yeah, okay, so
explain.
That chunk there, let me just solve this for a second. So solver will show you every instance, and we'll just use evolutionary. So on the right, there's this little reinstate button, which is grayed out right now because we haven't got any results to reinstate. But basically, that little green bar represents one run. And what it's telling me is that the bar at the top, the value on the left, the 486 right now, that's the displacement. So it's sorting this reinstate tab to should have had the best solution at the top. And so let's say I just like stopped the solver at some point. The reinstate genome basically will allow me to push the sliders back to the position that allowed for this result. So clicking reinstate, I'm going to move my sliders around, right? Reinstate, move my sliders around. So oftentimes if I'm doing this, I may run it once or twice, find the optimum solution, reinstate, click OK, and then run it again. Because I'm at that point starting from the child iteration of the first run.
Interesting, but
I mean, yeah,
it's hard to control.
It's really hard to control. I use this mostly for testing purposes. If I don't intuitively know what the best solution is, I will use this to help my intuition get better, basically. I think in the cases where it's, when you've got a really fixed thing to maximize or minimize, like Aloy had previously, it makes more sense almost. This is more just sort of design space iteration. What do I think might be the best solution without a true numeric, well, it's displacement, but there's lots of other variables involved here.
Okay, let's fly through that.
Okay. All right, I'm turning it back over to Aloy. We're going to do a little bit of form finding work. And I believe that's our last one for the day, or last couple of examples.
Yeah, and I mean, this is going to be a lot. So if maybe 15 minutes later, I don't want to drag on forever, but I want to make sure we hit all the important stuff. So I'll try to finish it all within the hour, and then maybe 15 minutes we can play and ask questions and things like that. But I just want to touch on some of the basics of form finding. The definition of that is essentially finding an optimal shape that reaches static equilibrium. And what do we mean by optimum? It means everything, minimal energy. Rob is, so by the way, Rob is still here. Yeah, minimal energy. So using a hanging chain, which you might have seen if you've gone to architecture school or visited Barcelona for the Sagrada Familia, is probably the purest example of that. The chain isn't any longer than it needs to be for that weight. It's exactly balanced for the weight that's put on the end of it. And so this is the most basic example of form finding. I will note though, and we'll see in these examples, that the form it's solving for is dead load. It's gravity. So you take the hanging model, you flip it upside down, now it can take gravity. And the idea is that if you've done this, a catenary arch takes mostly thrust and very little moment. So you want to see, and just as a general rule, catenary arch is the best shape for dead load, and then a circular arch is a better shape for wind load because it's normal to the surface. So the form that you get is a direct result of the loads that you give it. So this is why we are kind of introducing load cases a little bit. Although Karumba, I'll explain, Karumba has some limitations with form finding that make that load case function less obvious. So catenary hanging model, I think this image is just flipped, maybe. And this is showing an analysis model. You basically can model a bunch of catenary arches. In Grasshopper, there is a catenary object, and it's saying start point, end point, and what's the length of the chain. That's it, and it'll find the shape for you. So a very not a bad place to start, honestly. Like if you don't want to run a form finding analysis, but just make sure everything is a chain, like a chain off of a chain, it's not a bad place to start. This is a good example of the multi-hull. So it ends up being a rigid diagram. Not all form finding exercises end up as fabric objects, although a lot of times, you know, that's what you see a lot of it in practice. But oftentimes it represents something rigid. And so the rigidity and the way the nodes are connected to each other when you're doing the form finding is should be representative, or I mean, should is relative. So we'll go into that, but it makes a big difference whether the pieces connected to each other are allowed to rotate, or are they do they have some sort of fixity at the node? You're going to get a different shape. So you'll notice this one looks more dome-like than catenary. It could be a function of the nodes. It's a little hard to see what that model is, but the end result is actually a wooden diagrid. So it makes sense a bit. The general process is to take a unusual structure, not unusual, but kind of a complicated geometry. You have to mesh it, may not look perfect, and then run it through a form finding exercise to find a smoothed, minimal energy, neutral equilibrium surface. I found this on the internet. I couldn't really say it better myself, so I just grabbed it. But the process that this person's using, I think this is part of a research paper. Please don't come after me. I can't remember where I found this, but I did search form finding because I wanted to find some better images to explain where it, how you'd start it. So you can see that the vectors they're applying are going up and to the right. That may be the dominant direction, and that's giving you this hanging net. They're applying it in the other direction. They're also applying gravity. And so you can see the vector of your force changes the shape. And what they're doing here, which is very engineering, it's something an engineer should do, I think, is to always get the envelope of all the different forms it could take. You could flip it over and that could be your top. It could simply be the top and bottom surface of a shell, or it could just be a bunch of different analysis checks you're doing on a tensile membrane. The Block Research Group out of Zurich does a lot of really cool work with this. And this is an example of them using a hanging chain to come up with a shape and then translating that hanging chain into form work to make a concrete shell. It's very, very cool. This is Felix Candela's work. If you Google it, you'll see tons of shells like this, very lightweight, very minimal surface. I mean, it's not lightweight, it's all concrete, but it looks super, super light because the form has, concrete shells are mostly driven by dead load.
That's also the advantage. That's also the advantage of concrete shells, is that the weight of them is actually the predominant force on that structure. So therefore, if there's wind load, it's going to have it. It's not going to be ideal in terms of that form, but because the gravity is so heavy relative to the wind load, then it stands.
Yeah.
If that was made out of, in theory, like timber or something, you would have to have a different form.
Yeah, exactly. So keep in mind what it is, what is eventually going to become the form that you're trying to find, and is it appropriate? You know, what the loads you're putting in, is it appropriate? Do you need to do an envelope because it might be a tensile membrane, or is it a shell that is probably most likely dominated by dead load? And this is a rule of thumb. Form finding does not equal analysis. You still need to actually flip the shape over, apply the real properties, and test it for the loads you're getting. The load case input equals the resulting form. So the form isn't perfect for everything. It's dead load would give you one form. Point live loads are going to give you a different form. Wind load could give you a different form. And if you're trying to make a combo where you're combining all of them, you could have sort of something in between. And then each combination of different shape and loads needs a little bit of tuning in the form finding process, because it's not actually analyzing anything. It's just trying to create a shape, and you want to make some decisions that are appropriate. But most of the time it's relating one stiffness to another, Well, we'll show that the releases and the relative stiffness will change the form. And the last point is that just because you found a form doesn't mean it's super constructible. So the computer can solve it, but again, keep in mind what you're actually trying to build this out of. And if we have time, we'll show a little bit of Kangaroo. Karumba has a form finding engine, but I'll just say this up front. The Karumba's engine seems to be more suited for shells. There seems to be no way for you to really release it like a net. I could be wrong, but I was playing with it a bunch. Everyone in this room, we're used to doing form finding using Kangaroo, which is almost only using a hanging net method. And I've put them both in the same file, and you can see some major differences. It's really, really hard to get them to look even close. And I think the main issue is that in Karumba, it will not let you release mesh elements, one mesh quad to another to rotate, and kind of doesn't matter how thin it is.
Stability. It's solving that matrix.
So why won't it let you? Because I tried it with sticks too, and it still wouldn't do it. A bunch of sticks that are all released, it still looked.
Right, but that's unstable. It's in it, yeah.
Well, but it shouldn't be with the large deformation analysis. It should be able to handle it.
Even large deformation, it's not necessarily.
Yeah. So, but Kangaroo.
Yeah, but it's not using FEA.
Kangaroo is a physics engine, not FEA. It's not doing actual modeling. So here we go. We are going to, where's the Rhino? There it is. I'm going to open the Rhino file that is called save changes. No. Large depth form finding. And I'm going to open the Grasshopper document. We're going to start with the small. So 09 small Grasshopper form finding. The one thing I want to point out here, we'll show it in the large example as well, to make a mesh from random points. So all I'm doing here is just defining X and Y as like a general rectangle in space. And then I'm using a random button to generate a bunch of points within the rectangle. So I'm choosing 4, choosing a mesh size of 4, which is pretty small, but it's still large enough. From these 4 random points, I'm sorting them. I'm using this button called sort along curve. So it's sorting it along the rectangle I've created. And then this is the random mesh. This sometimes works, it sometimes doesn't. It's hard, you can't really control this, but for this example, it works really well. This is called Delaunay mesh, which is just trying to triangulate between a set of points. So I'll show you what that looks like. I'm going to turn off the end result. So it just tries to draw lines between a set of points so that you always have triangles. So it says triangulation. And it's not going to draw over itself for the most part. But if you have, once you start having things in 3D, this button stops working so well. But for this purpose, it really does. And if I were to change the size of the mesh, or, this is asking for a seed, I could change the seed. And I will here in a second, because this is just the Grasshopper one for the demonstration. I don't want to change it since I've already tuned it. So we made a mesh from that. We're using this tool called Mesh Edges, and I'm actually testing the edges to see whether they're within the polyline created from all the points going around the circle. So those are the outer edges. I'm testing all of the points to see with their midpoint. Oops. So these are all the edges. 1, 2, 3. I'm using, so edge 1 is understood to be the outermost edge of the mesh. Edge 2 is the inner, our inner edges of this Delaunay triangulation. You'll see in the larger examples that this it may look like it's very obvious what's what, but in the larger example, depending on how complex it gets, I'm testing to see whether the midpoint of the internal curve is actually inside this, or is it whether it's inside the boundary or it's at the boundary. So I only want ones that are 100% inside and not on the outside. Then I'm dividing by distance. And that's because I wanted to specify it exactly. You can also specify, you can just divide by a certain number. Everyone's used to that type of tool within Grasshopper. And remember, I'm splitting things up. So I've got my support points. I'm splitting up external edges along these division points. And internal edges are here with those points. And then I'm pulling all the points from the internal edge and the external edge, and then I'm putting them into the Karumba mesher, which is honestly one of the best meshing tools we've seen. It, as Nick mentioned, we always want connectivity, and it can be hard to. Oh, that one's throwing it off. It can sometimes be hard to make sure that you always have a node at that point. And we got a little weirdness over here, but it's all right. So in order to put into Karumba to do some form finding, initially, I want to say that the internal mesh is going to be less stiff than that internal seam, which is also going to be less stiff than the external edges. That's just a hierarchy. A rule that I'm making up for this demonstration, but you want to know what the different parts are that could have different stiffnesses and be able to define them separately. So I'm just going to show what this seed does. So 0 to 5. So seed again, this is why those random tools are like hard to control. So it's generating 4 points, but this seed will give me all sorts of different combinations. It's okay. We're just showing how this works. So we've got a pretty simple model set up there. And let's see.
Was one question.
Hmm.
Have you tried zeroing the bending stiffness for the shell and doing second order analysis in Karumba to capture membrane behavior?
No, because okay. So number one, we grabbed the form finding analysis from Karumba. So I wanted to use the large deformation analysis. Oh, why is it? No. Hi. So changing the bending stiffness is, where's your Karumba button? Wow, Nick has a lot of tools. Let me see. So I was actually, this has been somewhat of my gripe with the cross-section is modifying cross-section. I think what you're saying is you want to change this to 0, perhaps, on a shell. But the problem is it goes away when you choose shell. So I did the same thing. I opened this up and I said, oh, great, I can make it be a membrane by reducing the bending resistance. Because essentially what we want is a membrane, like something that can't take bending. We want it to just bend at the seams rather than
internally.
Yeah. But when you change it to shell, that option goes away. So it's something that I want to continue to investigate, but as someone that's been using Kangaroo for a long time, I have this other avenue. So if I'm not solving for a shell, I usually will use Kangaroo, but I hope that they make this an option. I hope they make that an option in the future. As far as I know, I don't know if this is first, second, or third order analysis, but we'll say that if you make this, okay, so it actually, oh, this may be because I try to put a release at the support point.
Yeah, it'll still run.
It'll still run. So this has an enormous amount of displacement. Okay, it doesn't like that. It wants this to be 0. It should work. This morning. So we can show the difference, but if you put in the first order analysis into the model and you put in the large displacement analysis, it is doing it in increments. So this is kind of exactly what we want it to do. And the resulting displacement from this should be a lot less than this because it can actually kind of take some bounce into it. Now, I don't know why this isn't working. I'm going to chalk this up to a little bit of me being on Nick's computer. So let me try grabbing a new version of it. So model, and we'll see that, is it, okay, what does it want? It wants it from this? That can't be right. No. Huh. Well, we're using Rhino 7. So let me just try it with Rhino 6. I don't know. I mean, it worked on my computer this morning. I was just testing. Open.
I have 6.
Oh, you might not have it.
I think I do.
Did we put it under downloads? No.
Not those downloads. Keep going to the top. Keep going up. There's not. Scroll up.
Oh, this one.
You right click, file open. It's automatic. That's 7.
Because I opened up
6.
I opened up 6.
It just says 7 in the top left of the.
I've got 2 windows open. This one's 6. Okay, we'll see. Do you have Karumba? If you don't, then no, that's true. It's okay. I have to admit, I don't know why that's not working then. This is the way it's set up and was working in Rhino 6. What could it possibly want? I guess we can try this. We can try this. Load case, max iterations. No. That's not what we want. Well, I can show you, I can explain what this tool does. Maybe you can put in the chat whether you've tried this on 6 or 7 and it's working for you, but this did work for me on 6. So it's asking for the model once you've assembled it. It's asking for number of load increments, and it's asking for a maximum displacement to try to scale the model to. And this part I find a little hairy. It's part of the tuning of the model that I'm used to just doing manually. But basically it's saying, if you want to make a dome that's form found, but you know that the height of the dome, the rise of it, you want it to be about 60 feet or something, you would put that into max displacement and it'll essentially form find the shape with large displacements and then scale the whole thing down to that max displacement. I think that works well. It was working well for simple shapes like a dome. But for something that has multiple ups and downs, it tends to scale every peak to the height, which is maybe not what you want. If it's 0, it's supposed to form find. If it's 0, then it's supposed to form find to the actual loads it has. And I believe that's more accurate. And I just watch the maximum displacement and tune it until the maximum displacement is where I want it. So I generally want to form find with actual loads and then tune it so that the displacement is where I want it to, rather than telling the model to scale it. But maybe somebody else has an example where you might want that. The weird thing about this tooltip though, which I read it a bunch of times, it's kind of confusing. It says if maximum displacement is greater than 0, then this is the prescribed value of the maximum deflection at the end of form finding. So then in each iteration, the maximum deflection is scaled to the maximum displacement that you set. If it's less than 0, the process is load controlled. Now, right now, it looks like it's automatically set to -1, so it wants to be load controlled. in Rhino 6, my computer did not like that input, and it only wanted 0. That's the only thing it wanted, and it wanted it wouldn't accept it as a panel. It wanted it as like a slider or something that's defined as a number. So it was extremely touchy about what was put in here. I don't know why this is working.
Maybe it wants to be a decimal point into a number. Like if you just type it like a slider into a number. I know that's stupid.
Yeah.
I put a number in between there, like
Oh, like this.
yeah, into a number. Yeah.
Problem is, it says could not calculate, use analysis, but that's this, and it doesn't, it's running, but you know, not great. Let me just see if I can get this to work, and then to see this to show something. Oh yeah, it's probably flying off into space, isn't it? The other thing is it's very thin, so yeah. Oh, it's there. Do you see that? Okay. So unfortunately, I had this tuned for this tool, but if we have to work with the simple analysis tool, let's try this again, see if maybe, is this solving? It's giving us the same thing as first order. All right, so this is part of the tuning. It's hard to see, but the structure is there. It's just flying off into space. Or if I change the shell thickness to 1, there it is. Okay, so it's very sensitive to what you put in as the shell thickness, but I was trying to replicate more of a catenary form finding, so having a very thin shell, so thin that, you know, maybe it's not contributing. Maybe if I change it to 0.1, that might be more, okay, that's a shell. And I'm also having this option where I'm trying to use Karumba and say, well, I want the beam at that midpoint to be something else. I'm going to say that that is maybe 0.2. So make it twice as thick as the shell, twice as deep. And the beams are on, didn't seem to change much. Interesting. Brings it down. Okay. Not so much, huh? So you'd rather, generally in form finding, you want a thin shell. And so you want to also reduce the dead load. You're not actually putting the dead load on this, you know, smaller version of the shell. 001. Wow. Oh, it's just struggling. Sorry, guys. This was working this morning on my computer. Okay, so we're getting some cool shell stuff, I guess. So we talked about load combinations. Let me just show you. I haven't totally set it up, but I considered setting it up for this demonstration. I just thought that this model already had enough in it. So one thing you can do, though, is set up a couple different loads. So we've got dead load. I have live load. And what I'm doing to select live load is just, again, having a random assortment of points that are chosen. You can see them down here that are chosen to get a point load. That's what I'm saying is live. And then wind load is a mesh load that's mesh load constant. I'm putting in the mesh. I'm saying it's local to the mesh, and it's generating point loads. And in all cases, I have the load itself and a factor. I've got the live load and a factor. Dead load has a factor. And then I'm using this value list again. So dead is 0, live is 1, wind is 2. But you can right click on it and say, make it a checklist. So this is a way you could combine loads. You could check all the loads you want and make sure that the factors of each relative to each other are like 1.2 dead, 1.6 live, and, you know, wind is not on. So if I were to turn This might be kind of an experiment. If I were to turn dead off, you can see it, it's flying super up through space because the live load is really, really high. Now it's trying to solve as if it only has the live loads on it. Again, if we were solving this as a hanging net, it wouldn't look so smooth. It would be a little bit more jagged between all those points. This is the tuning that it takes a little bit of time to get a shape that actually makes sense. You just keep an eye on the inches here of max deformation. If you know you're trying to reach a target height, you either have to change the, you have to tune the thickness of the material, which is the stiffness, or play with the load to get what you want. What I'm showing here isn't ideal because it's not using the third order, this large space. Oh wait, it's working now. Weird. Okay.
Just took that model in there, you should be fine.
All right, so the displacement here is a 0. Is it because I gave it the max displacement? Maybe this is something in 7. Huh, okay. So this may be a difference between 6 and 7. In 6, you can't give it a negative number, even though the tooltip asks you to.
Give it one.
But in 7, if you give it -1, it's going to solve for the load. Deformation is set to 1, and then we're viewing it in all these other ways. So, but where'd it go?
204 inches. Yeah.
So some weird things are going on here. Let's just 248 inches should still be visible.
Your elements turned on down there. I guess you do, right?
No, I didn't. Thank you, Nick. So that's 248 inches. Okay, great. We've got something working. And I want to view that shell with, what is it? I want to see displacement. So I'm not sure why I'm not seeing anything. Ignore this part. Essentially what I'm doing over here is just setting up another Karumba set, but the input mesh is deconstructed from the form finding. And I'm taking the shell from the input, the shell from the form finding, and actually giving it a thicker cross section. And then applying all the same loads. I'm actually just getting them from the first part, and the expression is just negative. So I'm flipping all the loads and making it real, and then actually analyzing it. In reality, you'd probably have a step in between where the loads you use to form find are tiny, and then the loads you use to actually check have the same relationship to each other, but are the actual values you would actually have. We're having all sorts of problems here. I'm not sure why this isn't showing the displacement. That seems really
Maybe
wrong.
deformation scale of 1, like just bump up the deformation.
It's really random. Let's try changing the max displacement to say 200 to 1,000. See if it actually. Aha. So this changed to meters. It might actually want meters. I say 1. It's giving me 100 inches. It must. I don't think would. Yeah, this has got to be centimeters. It doesn't make sense otherwise. So if I were to change this to allow more displacement, oh, it does not like that. Let's change back to a nice dead load. Nope. This is okay. This is the issue I was having with actually trying to prescribe the max displacement. It sometimes looked pretty, sometimes it looked like a crumpled piece of paper. But if I made it -1, it always reacted in a way that was expected. It looked right, you know, it's not trying to scale itself, but this way, if I change the dead load factor, make it a little, I make it 10 times more, it goes 10 times up. If I make the beam depth 1, it should, oh, I have beams turned off. It brings it down a little bit, but you don't see a dent in it the way you would if it was a hanging chain, because it's a shell. If I make the shell 0.01, oops. And the beam depth 1, dead load factor by 10, you can see once you change the geometry or you make any sort of change, you kind of have to go through all your settings again and make sure it's tuned. So unfortunately, this isn't going as well as I wish I could have shared my screen from my computer. Do you want to try again? You have it open?
I don't, but
Okay.
I can.
Let me show the kangaroo while you're trying that. Show you the kangaroo version, which is here, and that looks really nice. It always looks nice. So
Personally, I think the hanging chain method is as valid, but I think Aloy's right. It only works if you've got a heavy building.
mhm.
If gravity is the thing that's going to be controlling it, then you can go with hanging chain. If you got a light building, forget about it. You got to be concerned about other load.
Yeah, so in my former life as a facade engineer, I would use Karumba, or sorry, I would use Kangaroo to find the shape, and then I would take this and either send it to SAP or Strand to actually analyze it. So
I'm just going to try sharing real quick.
yeah,
see if
I'm
it
going to
works.
stop sharing. Nick's going to try to share from my computer. At least you could see what it's supposed to look like. It just looks black.
No, we're still on the Aloy's black screen.
Yeah,
guys,
Unfortunately, I don't know why my computer doesn't want to.
Well, it's worthwhile talking through the kangaroo approach,
Mhm.
I think.
Yeah. Okay, so let me talk through the kangaroo approach. We have 10 minutes left, so we're kind of right on time. I also want to show you the large approach. So we have the support points. Kangaroo, you can find, it's the other K. It's a physics engine. It has a bunch of goals. I will say some of these work better than others. But if you want to do a drainage analysis, there's a goal for keeping, I believe it's keeping points on surface or point on a mesh or something like that. Point on mesh, maybe it's over here. Goals mesh, yeah. So you can add a load to the vertex. You can add a pressure, so normal force. So I've used this in the past to inflate an ETFE cushion to a target height. You know, I'm just watching the pressure and then watching the top displacement. And when it reaches a point where the mesh looks good, then I actually bring it into analysis software to solve for it. So that's a pretty unique example, but ETFE cushions they're form found to the extent that you're trying to get a pattern and you're trying to get an inflated shape, but usually there's like a percentage of camber. There's a normal range between 10 to 17% at the maximum. So it's pretty easy to know what you're trying to get. Pressure would give you a different shape than, it looks like I was trying all three of these. I was trying to give you guys a good demonstration, but what I actually ended up with was a point load. So this is called goal. I believe it's just called load under goals point. It's just called load. Here's one called floor. The line goals are pretty interesting. There's some times where you want to just say, try to move everything around so that you end up with equal lengths. And that would be if you had a chain that you knew was going to be made of rigid members or a bunch of things that are all the same length. That's a fun problem to solve. Like, try to equalize the length of everything. That's what I mean about constructability. Because if you're actually trying to build a net, you probably want to buy a bunch of items that are the same length. or a bunch of tubes that are the same length that you put a string in between. And then using this goal, you can find a shape that actually would replicate that. And the goal we're using here is called length line. What it asks for is a line, and it says what length is it trying to reach. If you don't give it anything, it just tries to reach the starting length. And then how strong is that goal? So this is part of the tuning as well. We have the external edges, and I'm saying I'm taking the length of that, multiplying it by a factor of, this is a slider from 0 to 1, and I'm saying the strength of that goal is 1. The internal edges, I'm saying that they can be, that's trying to reach a length that's a little, it's 0.7 of its starting length. So it's longer than this one, and it has the same strength, which means that it's looser. So you're essentially, this is a way to change the stiffness of that line. And then for the internal edges, the way that I'm using it is I'm taking the mesh and I'm saying that these mesh edges, they have a length factor of 1. They are the loosest, but they have the same strength level as these 3. And if we were doing other goals, you might want to rank the strengths a little bit more. This is an anchor point, so I'm giving it support points. And what's nice is if you don't give it anything, it says location to pull the anchor to. If you leave it empty, it assumes the initial location. They also have this this can be useful. So it's saying, here's the point. You could say, I want to anchor it only in the Z direction, but it's allowed to move in X and Y. That probably would, you could set up a goal where you say the support points can move around, kind of like what Nick was doing with Galapagos. You could probably replicate here. The only thing you're missing is that this is physics-based and there are no actual loads. You can't really trust any, the load numbers are all relative. So it's not actually doing any analysis, but it does replicate, real life conditions like particles landing on a surface and then flowing around. That's something that's hard to replicate in any other controlled way or any other way. We've got support points, external edges, internal edges, and I try to mesh pressure. This one is just a equal load down, and I'm having that load goal. So the factor is 1, but we can increase that, and it should increase geometry. And then, the weight of it is so small that I'm changing this and it doesn't really matter. But if I make it 0.1, it flies up. So that's interesting. And you have to play with the relationship of load and stiffness to get to the shape you want, the shape you're expecting. Like Nick said, it doesn't really, you kind of have to know what you're trying to get to. The computer isn't just going to give you a design. You have to go in with a plan. The way that I've set this up in Kangaroo, in old versions of Kangaroo, the goal objects, you had to flatten this list. But what's nice is the newer versions allow you to give, so I have each goal in this entwined list. I put it in there without flattening it. That means that when you get the objects out, each goal is still in this branch. And that allows you to still maintain control of the, you can say let's see, the external edges is branch 1. So branch 1 is a bunch of lines. If I were to select those only, you can see that it's selecting all the external edges. If you wanted to take this immediately and send it into SAP through Grasshopper, this is how you would do it. At this point, you have all of your separate, goals, and you would send it to SAP. Something to note is the relative stiffnesses between the cables. That can be directly related to, you can basically assume that one cable, this is tension, the amount it's trying to shrink. So that's kind of like how much tension is in that cable. And that's why you actually have to take it to an analysis program to test it, because you have to see with the loads that we actually put on it, will the tension exceed the actual product, from a catalog that you have. So this is just giving you a shape. It's a minimal shape with minimal energy. It does not mean that this design will work. It gives you the output as vertices, and I'm just using this deconstruct option to give me all the Z components. I'm grabbing the min and max, and then with the bounds, and then using that to put into a gradient. And then the parameters I'm putting in are the Z components, and I'm coloring every point. And I did the same thing with the midpoints of every curve by the maximum deflection, which is 29 units TBD. Actually, let's try something. If I were to bake it, let's find out. I believe this should be 29 feet. The Kangaroo responds to Rhino. It's not like Karumba that has its own brain. It's kind of unitless. So I'm just going to bake this in. And then from the right.
Those are only internal curves. Those are the edges, by the way. You're not going to go for max there.
Right. But it'll be close enough, at least be in the ballpark. So I'm trying to measure, have somewhere around here or this 18 feet. Okay, so 29 feet is where we're ending up there. So yeah, let me just open up the large version. It's 5 o'clock. Let's show you the large version with Kangaroo, because that seems to be what's working. Wait, that's small. I just opened the same one, didn't I? Aha. So a couple kangaroo things to note here. When you put it into the solver, this button, if you toggle it to true, it'll keep iterating until it reaches a threshold. But if you see that it's still moving and thinking and you're like, that looks like it's close enough, you can change it to false and it basically stops solving and its current state. This button resets the geometry and resets the simulation. So this is, it's the same script, except that I've made a very large rectangle and I have 13 support points instead of 4. And I'm saying the mesh size is 4. So this one's just a larger version of the same script, which is kind of cool. I just think it's showing you what form finding can do and how quickly Kangaroo does it. You can also hook up Kangaroo to Galapagos, which we've done in the past, where move support points around to try to minimize the maximum deflection. So it doesn't matter what the deflection is, it's trying to get to the minimum version. But if you let what I just described, if you let Kangaroo run with that, all the points would just come together, probably. So you have to be careful when you're setting goals that it's going to follow you exactly it's going to follow you literally. And it does everything that you're doing. Every goal needs to be balanced. So are there any questions? I'm just going to play with this for a bit to show you guys how I normally would work with this. I'd get the shape fairly right, then go back, change the mesh size, then have to reset the geometry, and probably work with it. Are there any questions in the chat? No, nobody? I would be interested to know if you guys try anything with Thread, Galapagos, Karumba, Kangaroo. So you can see I've changed the mesh size. It means I've changed the input. Kangaroo, and 2.
One's tiny. It's a lot of points that you're trying to simulate right now.
All right, let me do 2.
Before was pretty good.
Yeah. Hang on. I got to get in between iterations and lock it.
Yeah, it can be useful to have that toggle to pulse in the plan with mesh iteration. So picturable.
Yeah. Yeah, Nick brought up a good point. I should have disabled the solver before I changed this. I tend to get
yourself.
Yeah, I tend to get ahead of myself because it works really well for a lot of stuff. And then I think, oh, I've got all the options, but no, you still have to, it will eventually get to a point where it stops. It's just
As it we're talking about zombie solving versus bouncing.
Do you want to do that? Actually, that,
All right. The
I'm not
last,
sure- I never use the zombies. That's why I'm like,
I mean, it's useful to point out, 'cause so
Mhm.
the issue that Alloy is facing here is that Grasshopper is trying to animate the form finding, right? It's trying to take the inputs that Kangaroo has and actually make a visualization from them, which can be nice to sort of understand what's happening with the script, but often. I'm just gonna set this to false to stop this thing doing its time, right? So the Kangaroo has a bunch of different solvers, but the way I try to describe it is it has a bouncy solver. This one is intended to show you animations from the starting position all the way through the result that has the least energy.
let's change that. Just that.
Yeah. Let's go back.
Lock the solver. Change it.
Or
to
8.
four. Yeah, no, 4 was pretty good. Then we can unlock and do it again.
So down here, we've got two types of solver. We've got the bouncy solver, which is the one we had on screen. This is going to animate for
Actually,
us.
that's just regular solver. Oops.
The zombie solver ignores the animation portion. It's only going to output the shape with the least energy. So it can be sort of faster sometimes if you're sort of letting it iterate a lot. If I'm going to use thread or if I'm going to try and use Galapagos with this, I'll almost always use the zombie solver because we basically want to get to the solution quickly as opposed to watch it get there. So we should just be able to replace the goals. We'll disable this guy and we'll just come back to here and you back to here.
Yeah.
Right. So in this case, we should get right to the solution, right? We're not waiting for it to bounce up at all. We're just going to get to the final position of the object, which can be faster if you're trying to iterate than having it.
Yeah. Why is the gradient not showing?
Apparently this guy doesn't give you trees. It
Yeah,
gives you
but
flat lists. Right.
that should. Coloring the points. It's weird. Anyway, yeah. Oh, nice.
The points are still being colored, but we lost the tree structure
Try changing to
to 1.
remove that to that. See what we get.
Okay. Cool.
Okay. So we lost some of the control over the objects, but then I think we have a little bit more. Yeah, how quick is that? Hey, pretty
Right.
quick.
Very snappy. Like you don't have to wait for it to bounce up is what I'm
Mhm.
getting at. It's nice to watch it do that, but
It's
the
very-
goal with the zombie solver is it's much faster than the bounce.
Pretty cool. So in conclusion,
Yeah, we love
Yeah.
form finding.
we love form finding. It seems like Karumba, when it works, is good for the shell. Like it gives you the shell thing correctly. I wouldn't even know how to go about doing that in Kangaroo. I think probably here with the hinge, but I have not had great results to finding that. It seems like you need to know which side is which, and it's trying to make an angle. So it'd be hard to actually model a shell with Kangaroo, and it's actually hard to model a chain with Karumba. So it seems like depending on what you're trying to form find, you should pick the appropriate tool for the task.
And always analyze it after.
And
All-
always analyze it after.
All of this is just a guess shape. It's not the right shape.
Does anyone have any questions? We haven't heard from anyone, really.
Well, text questions.
Oh, you're not showing yourself. It's me.
This Zoom keeps crashing on me.
I know.
Right, guys, we're at the end of our 6 hours. How about that? A lot of parametric structures for everybody. Thank you very much for coming today. We appreciate your attendance. We appreciate you coming to our masterclass this year. Feel free to contact us after if you have any further questions. I believe our emails are going to be available to you.
Or we'll share the PowerPoint.
Recording and the PowerPoint will both be shared. I'm not quite sure where that's going to be just yet once the symposium's done, but we'll obviously let everybody have access to it.
Maybe not immediately. We're going to edit the video and cut out all the parts where we're trying to figure out Zoom and we're having issues. But yeah, eventually the recording will be shared. We could probably share the PowerPoint a little earlier. And of course, if you're having any issues with the files, reach out to us. You should have access to that immediately. If anyone's coming to the hackathon or the symposium or anything, please introduce yourselves to us, and so that we can meet you in person. And
yeah, and then we can find some uses for Karumba even. We've
Yeah.
got those licenses, those pro licenses till the end of the month. So,
Yeah, the only thing I would say is, again, thanks again to Karumba 3D for lending us the licenses, as well as they also did mention for anybody who's interested in machine learning or big solves, they will be, you can get a cloud-based solver within for Karumba. So if you want to let something run for days and not affect your laptop, then you can do it. The other thing is Karumba, we will very soon be integrating Karumba with Shapediver. So the iframes that you see in the Karumba 3D website of the actual sort of with the exposed sliders to the various examples is as a tool called Shapediver, which is basically a Grasshopper 3D remote cloud-based solve. And so you can actually run Karumba 3D and expose that to the world in a web browser. So we haven't integrated that yet, but we will, because there are some tools that we want to use across the firm that require a solver to solve whatever engineering problem that we want to use. So that's available as well, or will be.
And I know we opened up the Slack channel and I saw some people joined it, but I think that's going to stay open for a while and everyone still has access. So if you try stuff later on, we'd love to see what you make with some of the stuff you've learned today. So
yeah,
please let us know how you're
feel free
using
to
it.
use the Slack channel, keep communication open. One question in here from Sanjay. Have you done GH Karumba for tunnels?
Yes.
Obvious.
Well, tunnel design, not tunnel design, but remember Sasha did that whole.
Just wonder, like you use like soil loads on a shell?
I guess the short answer, Sanjay, is we don't have anything on hand.
Yeah.
But was there a foundation load, something?
I think we could probably fake the loading if we're talking about
Yeah.
fixed like pressure from all sides, I guess is what a tunnel wants.
Yeah.
Right? Is that what you're getting at, Sanjay?
Pressure. Yeah.
Because we can't, the mesh loading allows local to mesh. So
Mhm.
not just global. So you can have loads that are sort of relative to the tunnel as it went around.
Yeah.
Which I think could,
And the pressure you could figure out from the depth from ground. I mean, that's
you could,
a parametric equation that you can relate to
certainly,
geometry.
you could have the mesh faces have a varying load based on their height or whatever
Mhm.
to mimic soil.
That's a really good problem, actually, because you can start with 2D analysis, basically sticks and lines,
Mhm.
and then move to a mesh analysis.
Just an extrusion.
Yeah, and then you kind of do what you do with the beam, right? So yes, that's a good problem, actually.
They
for-
do have a buckling of a
Truss.
No, they so let me just share my screen really quickly. The reason why we're not trying to reinvent or today we haven't tried to reinvent the wheel necessarily when it comes to Karumba, because they're very good about publishing a bunch of examples. Although between the metric and the imperial, we did have to make some tweaks. But if you go to Karumba examples, they have this buckling of 3D printing and fresh concrete. This to me looks almost like a tube, a tunnel. You might be able to hack this one, or just open up this example and see if there's anything in it that you can use. It says it's moderate difficulty, but I don't think this is any harder than anything we've just done. So it's, taking a circle and doing some stuff. So there's that. And then I also think that maybe this one, cross-section optimizer, it depends on what you're trying to solve for. If you're just trying to say, will this work, yes or no? Will this shell thickness work, yes or no, based on depth? That's just a pure simple analysis, but you could also probably hook it up to an optimization. Given a certain depth and diameter, what does the thickness need to be?
There's one more question in the chat.
Yeah, when doing shell analysis with buildings, do you use the same principle as the mass column example doing shell per floor? If you mean, I think in Karumba, all you'd have to put in is a mesh to making sure it has column loads, or making sure that they share nodes with the column,
Which Karumba does really well.
which Karumba does really well.
The mesh.
And then you have to give it a weight and a load, and it'll
Yeah.
automatically do the tributary area. You don't have to figure that out. I think the reason why Nick is showing that is because there's a lot you can do without actually analyzing.
The analysis is really good. I would say that example is a perfect analysis for Karumba and for Karumba, that is, because it does attract the mesh to the nodes. You can put the nodes of the columns directly in to the component.
Mhm.
And then you can do, gravity analysis, you can do diaphragm analysis, you can do all those things that you need to do.
Okay, well, as I estimated, 15 minutes past the time, but thank you guys for sticking around. Hit us up in the Slack channel if you've got any other questions. But yeah, thank you.